Welcome to the International Childhood Cancer Cohort Consortium annual meeting held by webinar this year. It's normally face-to-face, but the pandemic has made that not possible. However, we think having it this way will have its advantages because there'll be more of our members who can take part. They might not have been able to travel in any year. And we hope that there are people who haven't been involved with I4C who will find what's in this meeting of interest. We thank the Murdoch Children's Research Institute for hosting this for us, and we look forward to the proceedings, which are now coming up on the screen for you. What it will cover is first presentations from the large birth cohorts that make up I4C. Those cohorts have come together to provide adequately powered data and biospecimens to test hypotheses relating to the causes of childhood cancer using prospective data for the first time globally. And we will hear details of their cohorts and how they are progressing. Following that, there will be scientific discussions, some of which relate to findings from I4C that have already come from the consortium. And following that, we will also have presentations on the science more broadly associated with causes and prevention of childhood cancer. Some of this will relate to trends in the disease and what we know about childhood cancer. Some of it will be methodological, how we could improve the way we go about doing our work. I hope you find this of interest. If you do, and you would like to make further contact with the consortium, you will find at the bottom of the slide that's up presently a contact for I4C, and you can write to us there and let us know of your interest. If you have questions relating to any of the presentations, you can also send them there. We will refer them on to the particular speaker, and then they will get back to you with answers to the questions you've raised. Once again, we're very pleased that you're able to be with us and hope you enjoy the two sessions.
So MOBA is a large cohort. It's a family cohort based on trios, mother, father, and child. And as you can see, it's recruited from 1999 to 2009, with now more than 100,000 pregnancies. It's based on follow-up with questionnaires and the taking of biomaterials at the beginning, and also a follow-up on the registries. So the idea is to have a long-term follow-up and as many exposures and outcomes as possible in order to respond to many research questions. In this case, it's childhood cancer. So the data collection has been finished for all children up to the age of 8. The children are now between 11 and 21 years old, and as you can see, we did collect biomaterials, cord blood from the child, and blood sample, and also a urine sample during pregnancy from the mother, and also blood sample from the father, and several questionnaires during pregnancy and follow-up, mainly filled in by the mother, but also a questionnaire by the fathers, who were all asked in 2015. We do have ongoing data collection through electronic means. This is a nutritional questionnaire and mainly mental health, and then some short questionnaires every month when the children are 16. There's also a lot of ongoing data collection from the active participants in MOBA during the COVID situation. They are filling in questionnaires, and we are also taking blood samples. So the good thing about the Norwegian society is the existence of these mandatory registries. So there is no loss to follow up as regards childhood cancer, since we can link to the cancer registry using the unique personal identification number. And this opens for a lot of nested case control studies going back to the biomaterials to look at specific hypotheses. And we can follow also to some extent the other pregnancies of the same mother, and that opens for sibling control studies where you can compare pregnancies where the child later developed childhood cancer with pregnancies where that was not the case. And we do now have a lot of genotypic data for now 30,000 trios, and we will soon finish with 20,000 others. So this is a large resource for genetic research, and this is for epigenome-wide association studies, which is also building up. And to update you, we have had a lot of trouble with the data inspectorate and others who have been pretty insistent that we should get written informed consent from all 18-year-olds. And we have now finally landed on an agreement where we have a information procedure, and they can opt out if they don't want to participate. And this will, I think, ensure that we will follow the children through adulthood. We will. We have presently 227 cases of childhood cancer, and we will follow that up in a new linkage. So these are the cases by year of diagnosis and by their age when the diagnosis was set. And these are the types of cancer. This is then data that are in Australia. So we are ready to participate in new sub-studies of childhood cancer in collaboration with other cohorts. Thank you very much.
I'm going to give you a brief presentation on the Danish National Birth Cohort, but first I would like to thank Terry Dwyer and other organizers behind I4C for the important work they're doing in coordinating these activities. The Danish National Birth Cohort, DNBC, was recruited during 1996 to 2003, where a little more than 100,000 women were asked to participate while they were in their early pregnancies. Around 96,000 live-born children are being followed, and on average they are now 21 years old. The cohort has national coverage in Denmark, which we can see here, where every dot represents residence of each woman, and it draws up a nice map of Denmark. What we call the core project, the initially planned project, consisted of structured telephone interviews, self-administered questionnaires, blood samples, which could be linked to registers. So 4 telephone interviews, each lasting 10 to 15 minutes in gestation week 12 and gestation week 30, and when the child was 6 months old and 18 months old. And there were 2 forms that the women completed on paper. In the recruitment form, they were asked to complete questions or respond to questions on supplements and drugs. And in mid-pregnancy, a questionnaire was completed on dietary habits. 3 blood samples were taken and stored from very early in pregnancy, around 9-10 gestation week, and again around gestation week 24 to 25, and from the umbilical cord. We can see an overview here of all those components. All this information can be and materials can be linked to the national registers of Denmark. And this has relevance for I4C because the registers also comprise inpatient registers and cancer registers where ICD coded information on cancer diagnosis are recorded. There have been several later data collections when the child was 7, 11, 14, and 18 years old. At 14, the children completed a comprehensive questionnaire of diet and physical activity. And in 2014, during that year, all women received a questionnaire to follow up on their health and other information. The cohort is being led by researchers listed here, which is the Scientific and Management Group of DNBC, and Marie Nybo Andersen is a PI of the cohort, and others are Mads Melby, Cecilia Ramlau Hansen, and Katrine Strandberg Larsen, and Ellen Ågaard Nør. And me, myself, I am the deputy PI of the cohort. We've now been working for quite a few years with DNBC, and more than 600 articles in peer-reviewed journals have been published, and they can be found on the DNBC homepage. I would like to mention that there is a high compatibility between the DNBC and the Norwegian MOBA databases because of the common history of these initiatives and cohorts. And in particular for dietary exposures, we have done quite detailed assessments of the information on dietary exposures in pregnancy and found that they are highly compatible, and that has relevance for an ongoing project that we are doing relating dietary exposure in pregnancy to child's risk of developing cancer. And here we can see how cancer cases accrue in both cohorts up to ages 14, 15, and 16 years in the children. And we can see that the patterns are highly compatible between the two cohorts. Thank you very much for listening.
Good morning. My name is Milena Maule. I'm working at the Cancer Epidemiology Unit of the University of Turin in Italy, and I'm going to present the cohort NYMPHEA, an acronym that in Italian stands for Birth and Childhood, the Effects of the Environment. NYMPHEA is an Italian web-based mother and child cohort set up to investigate the lifelong health effects of exposures acting during prenatal life and early postnatal life. It started as a pilot study in 2005 in the city of Turin. It then extended to the rest of the country in 2007 and ended its recruitment in 2016, when about 7,500 pregnancies had been enrolled. All pregnant women that knew about the study, that knew Italian language and had access to the internet could participate in the study by completing online questionnaires. The first one was completed during pregnancy, and it was followed by questionnaires at 6 and 18 months of age of the child, and then at 4, 7, 10, and 13 years. And we are now about to release the 16 years old questionnaire. At 6 months, about half of mother-child pairs donated a saliva sample. NYMPHEA is still a young cohort, with the oldest participants reaching now 16 years of age. They are irregularly distributed in the country, most of them living in the northwest of the country in Piedmont. How do we identify cancer cases in NYMPHEA? We use two main sources. In Piedmont, we use the population-based childhood cancer registry of Piedmont that recorded incident cases of cancer in children since 1967 and in adolescents since 2000. To cover the rest of the country, we use the Model 101, a hospital-based registry of malignant tumors diagnosed in the 55 centers of the Italian Association of Pediatric Hematology and Oncology. This started in 1989 and recruits approximately 1,600 cancer cases in the country. In 2017, we linked NIMFEA with these registries and identified 11 cancer cases, among which 3 leukemias and 3 embryonal tumors. After joining NIMFEA, we proposed a study to investigate the effect of maternal folic acid supplementation before and during pregnancy and the risk of childhood embryonal tumors. The idea was stemmed from the observation that there were many embryonal tumors among the cases identified in the cohort NIMFEA, possibly because of the young age of participants. And it also had a secondary aim to study the feasibility of considering on all embryonal tumors together as a unique outcome for future studies. So far, 4 cohorts in Denmark, Norway, Australia, and Italy have accepted to participate in the study, and the estimated number of embryonal tumors is 106. The study should start soon. There have been some delays due to the tightening of rules for the transfer of data outside of Europe under the current GDPR. NIMFEA is also actively collaborating in international projects funded by the European Union, such as Life Cycle and Athlete. These represent cross-cohort collaborations that bring together data from multiple birth cohorts to facilitate studies on the influence of early life exposures on later health outcomes. The main deliverable of Life Cycle is the EU Child Cohort Network that has harmonized the data from 19 cohorts with about 250,000 children. The Athlete project aims at providing a comprehensive exposome characterization and the development of a human exposome toolbox. Of note, the analyses in these projects are mostly done using DataShield. This is a data analysis platform to perform analysis without physically transferring data. The major advantage is that the data from the different institutes are accessible for different researchers whilst remaining at the local sites. And similar approaches could be considered to address data transfer problems that are encountered in multicentric studies. And to end, these are our email addresses, and this is the website of the NIMFEA cohort. And thank you very much.
Now, I'd like to present the progress of the Japan Environment and Children's Study in 2020. As you know, Japan Environment and Children's Study, or JECS, is a nationwide birth cohort study that covers a wide range of Japan from north to Hokkaido and south to Okinawa. It involves almost 100,000 mother and child dietes, plus some fathers, and then it'll follow up the children until they become 13 years of age. We have measured many biological samples for many chemicals. For example, we measured metallic elements such as mercury, lead, cadmium, and poly and perfluoroalkyl substances, organophosphate pesticide metabolites, and environmental phenols such as parabens, bisphenols, triclosan, phthalates, and neonicotinoid insecticides, arsenic and POPs, and then AHR binding activity. We're trying to measure more chemicals in the biological samples, and then results going to come soon. And we've done home visits of 5,000 households, and then we measured VOCs, aldehydes, and acidic gas pollutants, and PM2.5 indoor and outdoor. And then we're going to measure personal exposure to VOCs and other gaseous pollutants in the sub-cohort study. And then we collected house dust and vacuum dust in 5,000 households, and then we measured mite allergen and endotoxin, and then we sieved the vacuum dust and stored for the analysis of like POPs and other chemicals. Here's the numbers of publications. It's growing fast. We didn't have any publication in the first 4 years, but from 2015, the number of publications is growing very fast. Here I show you one of the recent publications about association between maternal blood lead levels and birth weight. And we found that a birth weight decreased in 54 grams per 1 microgram per deciliter increase in maternal blood lead levels. And we are having many other publications. We haven't updated the dataset yet since the last presentation we've done in I4C 2019. So I show you the same data as we showed the last time. The numbers of ALL and AML and then other leukemia are in total 28 at this point. Here I show the CNS cancer case. The total number was 8. This shows solid cancer cases. The total number of solid cancer cases up to 3 years old was 44. The data for 4 years old is coming by this March, so we will report that to the I4C in very soon. Thank you for listening.
Today we talk about Campina's Childhood Cancer Consortium, the interim report from 2021. The Campina's cohort started in May 2016 and collected exposure of 100,000 pregnant women. Besides cancer, other variables were included as congenital malformation, myelodysplasia, and immunodeficiency. This is a place where you hold the programmed I4C cohort study, and this is in the down is the picture of the building for the laboratory data and the biobank. Concerning the materials and methods, we have 38 primary health care units that are currently participating in the study. We applied the questionnaires interviews at 2 moments, first in the third trimester of the pregnancy and after 6 to 15 months after the baby's birth. The applied questionnaire were inspired in I4C cohort models, and we include all these 12 items that were participating in the questionnaires. The 11 and 12 index were introduced on December 2017. The biospecimen collection with the pregnant venous blood is made in the third trimester of the pregnancy. The samples are refrigerated at -80 degrees centigrade, and the culture card is refrigerated at 4 degrees centigrade in the university. That is around 5 minutes from our center. Till today, we have 7,546 pregnant women ineligible, only 2 due to false pregnancy, and desistance 83. It is interesting to see that we have 52 that declined the previous consent, 13 that moved to private care, and 18 moved from city. Today we have enrolled in the first semester 7,000 pregnancies. The third quarter, babies born 1,713, and we will follow these babies till 18 years of age. Concerning the social demographic data, it's important to remember that this will work just to public health system. The age from the pregnant women range from 11 years of age, that's too early for me, till 50 years, the median 28 years. University level, 7.6%, single women for almost 42%, unemployed almost 60%, and the great majority living between $200 per month to $600 per month, half of the pregnant women. And the infrastructure, sanitation infrastructure, in our country is quite well in Campina when you have this number. Sewer infrastructure, 78%, and potable water, 82%. Considering the pregnancy characteristics, we have 15% of the pregnancies with infection. These are the etiology, syphilis with 40 patients, pregnant women. It's important to say that the COVID test was not introduced at this time, but now we have to introduce this. It will be necessary. The alcohol consumption, for me, is too high, 39%. We have to know about the general population that we don't know, but it's a high number, almost 40% alcohol consumption. Smoking doesn't call the attention, 13%. And another point that I would like to emphasize is more than 50% of the pregnant women has a cesarean procedure. And this is a high number, perhaps due to the payment that the health system pays more for cesarean procedures. Spontaneous abortion, only 1.3%. Considering the baby data, almost the same number male, female. Preterm, only 10%. I think that this number is similar to the general population in different countries. Cesarean, as I mentioned before, 51%. And underweight, 5% of the patients. That I think that is the same range when you consider first world and undeveloped world. In conclusion, even though the number of the pregnant women till now is relatively low, this study has gathered a strong public interest in the city concerning the quality of food and water and air. The main points to be considered and achieved during the year 2021 are to increase from 38 to 66 the number of the healthcare units participating in the study, to include in the questionnaires the in vitro fertilization that was forgotten to include, and the use of repellents as recommended for Zika for the pregnant women. And this we have to include, and also self-declaration. And again, to introduce an amendment to additional blood conception blood collection, mainly in the first trimester, to understand a bit more about abortion, and to expand, finally, the specimens, including buccal swab, cord blood, and placenta. The society involvement was translated through the Children's Environment Rights Advocacy Group that was established on September 16, 2019 in the Children Cancer Forum that was hosted in Campinas. This significant social engagement was inspired by an African proverb: if you want to go fast, go alone. If you want to go far, go together. That's why we are going together with the social society and the I4C leadership. Thank you so much.
Hello, I'm Woojin Kim from Korea. I will talk about a Korean birth cohort named Co-Chance. First, I will briefly introduce its study design. Our study started in 2015, and our target sample size is 70,000 pregnancies. Recruiting was supposed to be done by 2019, but some issues, including COVID-19, came up, so it was a little delayed, but it is almost completed now. We are planning to follow up these children until they become 18 years old. Our study consists of main and core cohorts. For the main cohorts, we follow their health outcomes through data links from the National Health Insurance Service, which covers the whole population in Korea. For the core cohort, we follow 5,000 children's visits to regional centers and make them take exams at each center. Some children recruited in 2015 became 5 years old now. The Korean government is very interested in this project, and the National Institute of Environmental Research takes a very important part of our study, since policymaking is their important goal. And regional centers have a role in recruiting pregnancies and follow up the children. This map shows the regional centers, which covers the whole country. Our main hypotheses include health outcomes, which focus on pregnancy outcome, age, development, but also another subgroup focuses on environmental exposure itself. Now, our current status of the study. We made protocols for 5-year-old children, and the physical and laboratory tests include a development test and sampling of blood and urine. And it will continue to until they become adolescent. In more detail, we collect questionnaire data, environmental measurement in selected homes, and measure heavy metals, phenols, and phthalates from urine samples. Now, people in the National Institute of Environmental Research are doing quality control, and we are planning for our data analysis this year. Our first subjects will be on environmental exposure and pregnancy outcomes. We are also planning for additional measurements and omics study. Finally, the plan for ascertaining childhood cancer. We collect environmental exposure data and health data directly from children in core study, and they are about 5,000 But this number is not enough for children's cancer ascertainment. For another 65,000 children, we will link with Children's National Health Insurance Database. Our health insurance database contains eligibility data, disease code in ICD-10, so that we can define childhood cancer. For the private information issues, people from Ministry of Environment and from National Health Insurance Service are in discussion now. Childhood cancer codes classified into 14 subgroups. This cohort profile paper is the only one paper published until now from Cochen's group. But we recently set up the plan for the analysis. We'll be gearing up for the first subjects, which is related to environmental exposure and pregnancy outcome, and then broaden our study subjects about environmental influence on children's health. Thank you for your attention.
Thank you for the invitation. I am Vincent Jadou. I am PI of the Generation R study and also project coordinator of the Horizon 2020 Lifecycle project. I want to discuss the creation and coordination of child cohort networks and especially focus on the power of international collaborations. Of course, you know very well that low birth weight is related to various outcomes of health in later life. Low birth weight is related to cardiometabolic disease, to type 2 diabetes, to hip fractures, but even with income and marital status is related to having a low birth weight. This leads, of course, to a lot of research questions. The developmental origins of health and disease suggest that early life is important. It's important for short-term outcomes, also for outcomes later in life. This leads to the concept that early life gives also opportunities to promote health outcomes during the full life course and to prevent disease development. In Rotterdam, we have the Generation R program. The Generation R program has 2 cohort studies. The first cohort is a pregnancy cohort of 10,000 parents and children, now aged 18 years. And recently we started with the preconception cohort, a smaller cohort of about 5,000 mothers, partners, and their future children. These are both multi-ethnic populations in the city of Rotterdam in the Netherlands, and they have detailed measurements in both parents, in fetal life, and in childhood. The studies are characterized by multidisciplinary phenotyping, including advanced imaging techniques like embryonic ultrasounds, MRI studies on a population-based level, and extensive biobanking across the full life course. Generation R is not, of course, the only cohort study. Many cohort studies have been started in the last 20 to 30 years because of the findings that early life is important for health outcomes throughout the life course. This leads to unique opportunities for innovative research and on the effects of early life stressors, health and healthy start and life course health trajectories. The collaboration between cohorts enables studies focused on geographical regions, mechanisms, and subgroups with, of course, much more power than any specific study itself. We have a lot of experience with multi-cohort analyses, and it appears to be that there's some confusion about the arguments for and against these kind of collaborations. Clearly, there are very strong arguments. A matter of efficiency and cost, there's a unique opportunity to use the available data. A lot of cohorts who have a lot of data which are frequently not optimally used. You have more power, you can identify specific pathways by using subgroups on interaction analyses, which requires bigger numbers. You prevent publication bias because you can also use in bigger groups of cohorts the yet unpublished data. And there is a better potential for external validity because you have more numbers, more geographical spread, and more countries involved in these kind of multi-cohort studies. But you have to also realize that bad study designs cannot be solved by multiple cohort analyses. So the issues of internal validity, like selection bias, information bias, and confounding, can clearly not be solved by just putting more data together. We have established a life cycle project. This is an Horizon 2020 program focused on early life stressors and the consequences across the full life cycle. First, we want to establish the EU Child Cohort Network. I will discuss that later. We identify novel markers for early life stressors affecting health trajectories, and we want to translate findings into policy recommendations. The life cycle project is now in its 4th year. We have an extension for about 6 to 12 months. So we have 1.5 to 2 years to go. The main aim of the life cycle project is to establish the EU Child Cohort Network. The EU Child Cohort Network brings together a lot of different cohorts throughout Europe. You can see the blue circles, which are actually the participating cohorts, and the red circles are those cohorts who do not participate in the life cycle project itself, but will be or have been invited to participate with their data. At the end, we do not have one data set and at one specific center. The power of the EU Child Cohort networks that it harmonize data across different cohorts throughout Europe and also in Australia, and enables federated analyses by using data of these different cohorts. So actually, at the end, the data do not come to the researcher, but the researcher comes to the data. When we have this network, we focus on specific exposure mechanisms and adaptations, and mainly focus on identification of windows of opportunity across the full life course to prevent diseases. You can see here a conceptual figure starting in preconception, then into pregnancy and birth, in childhood, adolescence, and young adulthood, and then the arrow goes back to the preconception period clearly. We focus on different early life stressors, mainly socioeconomic status, migration, urban environment, and lifestyle. We develop with Martina Vrijheid, the next speaker, an exposome model by including more different exposures in one model. We focus on specific epigenetics or DNA methylations as mechanism. We focus on fetal and childhood developmental adaptation mechanisms, both in the cardiovascular system, in the respiratory system, and in the brain development. And then we have the cardiometabolic, respiratory, and mental health, risk factors or outcomes in childhood, and the related diseases later in life. This is the main concept, and of course, this leads to a lot of different potential research projects or papers, and this is in the phase what we are in now. Many projects have been started by using the EU Child Cohort Network. I already mentioned that the EU Child Cohort Network does not bring data to the researcher, but enables data use by a specific researcher and then use data of different sites across the globe. And how it works is the data remains in each institution. It enables access, of course, with permission for an external researcher, and then the data from these different sites comes together at an analysis computer, or the results from these data analyses comes together actually, and then the results will be sent to the researcher. So the researcher will never get access to the original data or all the files of study participants. These persons only get access to the results of their statistical analyses. This is important because the EU Child Cohort Network actually is in the forefront of developing a system which takes into account the GDPR, the European regulation, and consent restrictions, which are often there in European cohorts. And that's mainly the reason why the data stays in each institution. So the main deliverable of the lifecycle project is the EU Child Cohort Network. And just to summarize, the EU Child Cohort network harmonized over 100 variables in more than 20 cohorts, which includes actually 350,000 children and parents, and this number is still increasing. And these are the really detailed data, also blood pressure, obesity, BMI trajectories, but also, of course, detailed exposures. We developed a new and open variable catalog, which is actually the EU Child Cohort Network variable catalog. You can access this by the Lifecycle website. We enriched many cohorts by new integrated exposure or exposome variables. This work is led by Martina Vrijheid, who's the next presenter in this session. And main advantage is actually that it's a GDPR-proof federated data infrastructure using the R application Data Shield, so it's a free application. And DataShield is now still developing because of Lifecycle and other recently started projects. We developed actually an infrastructure for governance, for sharing analyses and results between these different sites and cohorts. And actually the good news is that all protocols for harmonization, for setting up the servers, for installing the data on a server, for working with DataShield are available through our open website. These are just accessible for everybody. And we also have a YouTube channel for instruction videos. And what we also think is that it's very important that the EU Child Cohort Network is sustainable after the life cycle duration. And this seems to be successful because we have different networks, including the You Can Connect, Athlete, Longitudes, but also Nutri Program or End Obesity, which has been recently funded, make use of this EU Child Cohort Network, which is very good, of course, because then this enormous amount of work will be sustainable beyond the duration of the life cycle project. The life cycle project, and especially the EU Child Cohort Network, have been described in a paper in the European Journal of Epidemiology. It is an open access paper, of course, and you can simply look it up. And if you have questions, please contact me, whether you can join or do need information about the project. Just as a summary, please realize that collaboration between birth cohorts gives great opportunities for innovative research on healthy start. Collaboration helps classical epidemiological studies in many ways, but always realize that it does not lead to a better internal validity. So the design errors or mistakes, which are part of course, a lot of different cohort studies cannot be solved by just increasing numbers. There are other advantages which have been discussed.
Hello, my name is Martina Vrijheid. I work at the Institute for Global Health in Barcelona, and I would like to thank the organizers of the webinar series to invite me to participate. I was asked to talk about the exposome, and I will in particularly show you how we started to implement the exposome concept in birth and child cohort studies in Europe, based on the Helix project. Helix is a project that was funded by the European Commission Framework 7 project, and our aim was to provide a wide coverage of the exposome during vulnerable early life stages and to link that to child health. We implemented the exposome in 6 European birth cohorts, 6 existing cohorts, through a sort of nested design where we used the entire cohorts to estimate exposure to many urban exposures, urban environment exposures. And then we selected from those entire cohorts a sub-cohort where we did much more detailed measurements of many chemical biomarkers, omics markers, and we implemented a common follow-up across the 6 cohorts to measure health outcomes in the children. We also had detailed panel studies for personal monitoring and repeat biological sampling with a particular aim to look at the variability in omics markers and in exposures. So in terms of what we measured around 87 prenatal exposures and 122 childhood exposures across many different domains of the exposome. And this included urban exposures such as air pollution, the built environment, noise, traffic, tobacco smoke, and also lifestyle exposures measured by questionnaires, and a range of chemical pollutants measured through biomarkers in urine and in blood, both in the mothers and in the children. Then for the internal exposome, we measured molecular markers in 6 omics layers, ranging from the DNA methylation and transcriptomics using untargeted approaches to more targeted approaches that we used for measuring proteins and metabolites. And these data are available for collaboration. So I've put a link here in case anyone is interested in setting up collaborative work using this database. Now, as part of Helix, one of our first aims was to describe the correlations and the patterns in these exposures and also their determinants. And because this is important information for setting up the statistical approaches and also for interpreting results. So here's just a visualization of all the exposures that we measured and their correlations. And you see that the highest correlations are found within exposure groups, but there are also many links between different groups of exposures. For example, here in these chemicals that are present in personal care products, or here where we see all the urban environment exposures clustered together. And this is described in a series of papers focusing on the correlations and the patterns in exposures, but also on describing the determinants of these exposure patterns. And in particular, this socioeconomic position and diet in terms of their relation with exposure patterns. In the second part of the study, we then try to associate these exposures to their molecular signatures using the omics data that we collected. And we did that, first of all, by building a catalog of all the associations between exposures and omics markers. So here we tested many associations, and we tried to visualize that again by building a network of associations in which we find clusters of exposures and omics markers that are associated. One of the main conclusions of this work is that the prenatal exposures seem to be associated mainly with DNA methylation. So we see these permanent signatures of the prenatal exposures, whereas the childhood exposures show associations across the different omics layers. We also use this omics data in other ways. Here I've put two examples. The first one, in the first one, we go into much more detail into one specific exposure, in this case, tobacco smoke, and we look at the multi-layer omics signatures of tobacco smoke, where we find, again, DNA methylation related to maternal smoking, and then related to childhood secondhand smoke exposure, we find certain metabolites and proteins that are seem to be relevant. Also, the other example I've put here is one where we use the omics layer, in this case metabolomics, as an intermediate between the exposure and the health outcome. And in this example, we related prenatal exposure to perfluoroalkyl substances, so the PFAS, with liver injury in children, and we find that alterations in key amino acids and phospholipid pathways were associated with the exposure and also characterized the outcome, the liver injury. The third part of the project was about linking the exposome to the child health outcomes that we measured. And the first question we asked us is, which are the exposures most strongly associated with the child health outcomes? So out of all these exposures we measured, which ones are most associated? And we took an analysis approach that used different analysis techniques, different steps. In the first step, we ran an XWAS, which is where you associate each exposure with the outcome using a correction for multiple testing. A second step then used variable selection methods, such as the elastic net or the DSA algorithm, to select a set of variables that best predict the outcome. And in some of these publications, we also used clustering methods to group together participants with similar exposure experiences. So here is a quick summary of the results of those papers. I won't go through each in detail, but we see that some exposures were associated with more than one outcome, for example, smoking, outdoor air pollution, and some of the chemical exposures like the phthalates or the parabens. And we also have some exposures that seem to be more specific to a particular health outcome. There are some advantages of analyzing data in this way, in this exposome-wide approach. And the first one is that this gives a very systematic and comprehensive screening of many suspected risk factors. So it gives an overview of everything. It corrects for multiple testing, whereas if you would publish each of these exposures or exposure groups in a separate paper, you would not normally do that. It avoids publication bias because we publish all associations, including those that are null associations. We correct for confounding by co-exposures in the multiple exposure models. And it's a type of suspect screening, so you may actually detect novel risk factors, exposures that were not maybe the main focus of the study. And ultimately, this approach could be useful for priority setting, whereby we could envisage intervening on the agents that are most likely to be associated with health. Now, of course, there are some limitations and challenges that we faced. The first one is that in order to actually rank exposures by their importance, we have to bear in mind that this is difficult because these exposures are measured with different levels of measurement error. Especially some exposures that were not so well measured may suffer from false negative bias. And this can be solved by, sometimes by error correction modeling, and of course by improving the accuracy of all exposure assessments. We also know that these methods are prone to false positive bias because of the high correlations we find, especially within the exposure groups. And again, there are strategies to help overcome this limitation. We can try to integrate more a priori knowledge, and we should certainly look at replicating the first results of these studies. In our particular study, we had some potential for reverse causality bias because our exposures and outcomes were measured, the childhood exposures were measured at the same time as the outcomes. And so we're implementing now a prospective follow-up to overcome that limitation. And power and sample size, of course, are an issue when we run so many different comparisons. And here it is important to work towards larger studies, reduction of measurement error, and also methods that try to reduce the dimensions in the exposure data set. There are also some issues that we have not yet been able to tackle in these studies, but that are certainly on the agenda for future studies. And this includes looking at interactions between exposures, looking at integrating methods for evaluating combined exposures and mixtures, looking at integrating further complexities in the data in terms of the causal structure, the data hierarchy, so the hierarchy in the exposure data, and repeated and longitudinal measurements of both exposure and outcome. Also, our approach was very much based on suspect exposures. We did not go fully untargeted or non-targeted. These methods were not available when we started Helix, but now in recent years, high-resolution mass spectrometry methods are becoming more and more available to also integrate and include more of the unknowns. So I'm very happy to say that in the last H2020 Exposome call, we were awarded a new project called Athletes to advance on some of these issues. So you will hear more about this in coming years. Athlete is part of the European Human Exposome Network. So this is a network of all the projects funded under the last exposome call of H2020, which includes 9 big exposome projects. So there is a lot of investment going into exposome research now in Europe, and I think we will see some very interesting results in this area in the coming years. And then finally, I would like to acknowledge all my collaborators, because this has been an enormous effort with many people from many teams involved. And thank you very much.
Good morning, good evening. It's really an honor for me to report some of the results of the I4C projects relating to childhood cancer. My name is Aura Paltiel, and I'm from the Broad School of Public Health at the Hebrew University in Hadassah in Jerusalem, Israel. When we think about the exposures that we would like to study related to childhood cancer, they're spread over a vast territory of preconceptional events, intrauterine exposures, peripartum events, birth characteristics, and the early childhood environment. The preconceptional exposures include environmental and occupational exposures of the parents, the genetic makeup of the parents. The intrauterine environment is influenced by maternal behaviors as well as illnesses and other placental and intrauterine conditions. The peripartum factors include the type of delivery, the mode of delivery, like cesarean section versus vaginal delivery. Birth characteristics which have been looked at include the child's sex, the child's weight, the child's length, as well as others. And the early environmental exposures, including factors that are related to socioeconomic status, as well as family size, birth order, the infectious environment, as well as other environmental exposures. Perhaps some of the easiest exposures to look at in relation to childhood cancer are birth characteristics like birth weight, and also the early childhood environment when it comes to exposures such as family size or the child's position in the family. Birth order are actually very easy to measure. But some of these birth characteristics don't just reflect events after birth. They actually go back in time and reflect intrauterine or even preconception factors such as genetic factors, etc. So when we study factors such as birth weight, we're really looking at a very long window of possible exposures of the parents as well as the fetus itself. So the first study I'm going to describe to you is our study on birth weight and childhood cancer. And certainly we were not the first to think about this association. It was first described by McMahon and colleagues in 1962, and they looked at death certificates and found an excess of childhood cancer deaths among larger babies. And similar studies were performed in the mid and late 60s. Eventually, by the 2000s, there were enough studies to actually pool into a meta-analysis. And you can see that for acute myeloid leukemia in children, the results were extremely heterogeneous. Whereas for ALL, there seemed to be a tendency, especially among the larger studies, that pointed to larger babies or higher birth weight being associated with a higher risk or rate of acute lymphoblastic leukemia. So we decided to pool the studies of the I4C. There were 6 participating cohorts from 4 continents: North America, Europe, Asia, and Oceania. These cohorts are of various sizes, and they were formed over many decades. So CPP started in 1959, and the Scandinavian cohorts, DNBC and MOBA, recruited up until the 2000s. And the cohorts were of various size and had various numbers of cancer patients. We knew that there were many, many determinants of birth weight, and some of these were related to the child, for instance, their gestational age, their length, their gender, also where the pregnancy took place, at what altitude, and whether they were firstborn child or not, and also factors related to the mother, for instance, socioeconomic status, ethnicity, smoking, gestational diabetes, and also maternal anthropometric factors. And two factors in particular were very important to us and really spurred the study, and that is the rising prevalence of maternal obesity. These are rates from England, showing increased rates of maternal obesity and overweight into the 2000s. As well, we know that many mothers, and in the US it's about 50%, 48%, have a greater than recommended gestational weight gain during pregnancy. So these two factors we know are related to birth weight, and the question is whether these secular trends of increasing maternal obesity or increasing gestational weight gain are going to contribute to increased rates of childhood leukemia. So we designed this full cohort study. We ascertained cancer cases from all the children in the 6 cohorts. That's 380,000 live-born births. And this was after harmonizing the data for all the covariates and exposure variables. We included all the live births from ALSPAC, CPP, and TIHS cohorts. But for MOBA and DNBC, all cases were included, but a random sample of 10% of the non-cases were included as per the stipulation of these cohorts and their data transfer agreements. For the JPS, the Jerusalem Perinatal Study in Israel, we include all infants who had gestational age recorded, and that was about 21,000 infants in the birth weight analysis. And in the birth order analysis, we included all infants in the JPS, which is 92,408. We excluded multiple births because of their relationship with low birth weight, and we excluded children with Down syndrome because of its association with childhood leukemia. The analysis was carried out using Cox proportional hazard models. We adjusted for multiple confounders, potential confounders. We studied interactions when we thought they were necessary, and we dealt with missing covariates by using multiple chained imputations. Ascertainment of cancer was done differently for the different cohorts. So for 4 of the cohorts, ALSPAC in the UK, DNBC in Denmark, JPS in Israel, and MOBA in Norway, the source of the cancer cases was the National Cancer Registry. For TAHS, the linkage was with the local Tasmanian Cancer Registry. And for CPP, clinical criteria for cancer diagnosis were used, including summaries, clinical summaries of the patients. And each of these was reviewed by 2 board-certified pediatricians. We classified tumors into 4 categories: all cancers, leukemia, using the ICD-10 and morphology codes, acute lymphoblastic leukemia, and non-leukemia cancer, which was all the cancers that were not leukemias. Before I go on to describe the associations that we found, I do want to show you that we looked very carefully at the covariates, and here you can see just a partial list of covariates and their association with birth weight. So we see many, many maternal factors, both biological and behavioral, that are associated with birth weight. We see some paternal factors that are associated with birth weight, specifically paternal age, some fetal-related factors such as gestational weight, age, and whether the child was firstborn or not. So all of these, plus many more, were considered as potential confounders in our analysis. And we published a study in the Pediatric and Perinatal Epidemiology Journal in 2015. The analysis included 377 children with cancer, of whom 115 had leukemia, 98 acute lymphoblastic leukemia, and 262 had non-leukemia cancers. The main finding was that birth weight was indeed associated with childhood cancer with a hazard ratio of 1.26, which did not cross the 1, and this was after adjustment for multiple covariates, including gestational age, the sex of the child, the age of the mother, etc. One of the important things was to look at whether there was heterogeneity by cohort. And here you can see the association between each 1 kilogram increase in birth weight and cancer diagnosis. And you can see that all of the cohorts had a hazard ratio which was greater than 1. For DNBC, it was very close to 1, but there was minimal heterogeneity among the cohorts, although none of the cohorts has sufficient power to describe a statistically significant relationship between increasing birth weight and childhood cancer. And here you see the pooled data, the pooled hazard ratio with the statistically significant confidence interval. So as I said, we looked at 4 cancer outcomes: all cancers, leukemia, acute lymphoblastic leukemia, and non-leukemia cancers. You can see that for all except for the non-leukemia cancers, we have a more or less monotonic relationship with a significant Spearman row that can be used as the test for trend here. And this was after adjusting for gestational age and the sex of the child. For non-leukemia cancers, this association was not clear and not statistically significant. However, when we looked specifically at non-leukemia cancers, what we found was an interaction between age of diagnosis and birth weight and its relationship with these cancers. So for children under the age of 3, there was no association, an inverse association, which was not statistically significant. However, for all the metrics that we looked at, a large, high birth weight above 4 kilos, or the top 10 percentile of birth weight, or birth weight as a continuous variable, there was a statistically significant relationship between these birth weight metrics and childhood cancer, which was not leukemia. If we compare ourselves to the literature, then certainly the point estimate for our hazard ratio was within the confidence interval of one of the largest meta-analyses, so in the same ballpark, so consistent with the literature. So if we look at what the study added, we confirmed the birth weight cancer and birth weight leukemia association, even after adjusting for child sex and gestational age. We found effect modification by age of diagnosis for non-leukemia cancers, where the relationship was noted for cancers diagnosed greater than or equal to 3 years of age. There was minimal heterogeneity among the cohort. I didn't show you this data, but maternal obesity and weight gain were not significantly associated with leukemia or cancer, but they also did not alter the association between birth weight and cancer outcomes. This may have been a problem of power and small sample sizes in some of the cells. And so this is something that the I4C needs to carry on and investigate once new cohorts are added and cancer numbers are increased. Our results were comparable to the literature more or less. And maybe the most important outcome of the study was that it enabled us to construct the I4C data set and fine-tune the covariate signature that could be used for future I4C analyses. I want to move on now to the second question that we looked at, which was the question of whether birth order was associated with leukemia in children. So the background to the study is, as you probably all know, Mel Greaves and others have stated a hypothesis that early infection exposure is protective for the development of future overt leukemia in children, meaning that delayed infection causes delays in the development of a robust immune system. And so when viral or bacterial exposures come along, the child may not be able to deal with them properly, and there's an unregulated or dysregulated immune response, which may predispose to leukemia in the right setting, especially given the right genetic background. So we also know that birth order and SIP size are considered proxies for exposure to infection. And already, again, in 1962, McMahon and Newell, and then Stark and Mantell in 1966 showed this almost monotonic relationship between increasing birth order and decreasing risk of childhood leukemia. And in fact, in virological and bacteriological studies based on swabs or serology, there does seem to be a relationship between increasing birth order or increased number of siblings and exposure to various viruses, bacteria, and even to protozoa. So the using birth order and SIP size as a proxy is a reasonable assumption. However, the literature was not 100% clear, and I would say there was a seesaw in the literature regarding whether birth order is a risk or protective factor for childhood leukemia. And in fact, a summary of studies published between 1997 and 2007 showed a high variability. Some showed increased risk, some showed no change in risk, some showed decreased risk. And for ALL, the distribution was sort of 40% increase, 40% no change, and 20% decreased risk. Having said that, some recent studies have shown, again, a clear monotonic decrease in risk of all childhood cancers, CNS cancers, and possibly ALL and Wilms tumor with increasing birth order. So against that background, we also had some other concerns which spurred this study and served as a rationale and case for action. The first is the increasing incidence of childhood cancer, both observed both in the US and in Europe. The second is the secular trend of decreasing family sizes in the West, where the 1 and 2 child family are becoming much more common, whereas the 3 and 4 child families are becoming much less common. The third element in the rationale is that we know that in case control studies, there's a high degree of bias regarding participation by birth order. So children or even adults of different socioeconomic status and different birth order may choose differentially to participate both as cases and as controls in case control study. So we did this study looking at birth order and childhood leukemia. It was published in the International Journal of Cancer in 2018. You can see again, we had over 380,000 members of the cohort participating in the study. The number decreased because of the 10% sampling of non-cases from the MOBA and DNBC cohort. The median years of follow-up, the mean years of follow-up was 12.3. 68% of the children were later born and not first born, and the mean SIP size was 1.8. As you can see, the total number of cancer cases had increased since our previous birth weight analysis because of new linkages with the cancer registries. So we had 643 cancers, 185 leukemias, and 136 ALL. So in terms of results, we did see this monotonic decrease in risk of all cancers and acute lymphoblastic leukemia with successive birth order. We found this relationship more or less in all 5 cohorts that were studied. And this is the pooled analysis. So very little heterogeneity. Just one cohort had a hazard ratio above 1. If we look at birth order as a continuous variable, there was a statistically significant inverse relationship between increasing birth order and leukemia overall and ALL. So a 16% reduction in risk of ALL for each successive birth. And when we truncated them to less than or equal to 6 births, the findings were even stronger and were highly statistically significant. Interestingly enough, we wanted to look at whether birth weight and other factors modify the relationship between birth order and leukemia. And so in this analysis, you actually see 2 factors, 2 effect modifiers. One is paternal age, and the other is birth weight. And what we found in this analysis is that babies born with low birth weight, very low birth weight, less than 3 kilograms, and especially those of older fathers over the age of 30 or over the age of 35, were especially at decreased risk of developing acute leukemia in childhood. You can see a hazard ratio of 0.26 and 0.1. These are based on small numbers of cases, but was highly statistically significant, as were these formal interactions. So in summary, this study confirmed that higher birth order confers a protective effect against leukemia, and it is compatible with the delayed infection hypothesis. So we see evidence of postnatal environmental exposures on childhood leukemia risk. But we also found that birth order, that the effect was further modified by low birth weight, meaning that there are probably influences of the intrauterine environment, and was also modified by father's age. And we know that increasing paternal age may be associated with increasing rates of spontaneous mutations, as well as accumulated environmental exposures in the father. So let's just look for a minute what is beyond these I4C studies and results on birth weight and birth order. So the first thing that I would mention is that these associations with these exposures, both birth weight and birth order, are not just limited to childhood cancer. Increasingly, we're seeing a literature related to birth weight and adult cancers, controversial in terms of breast cancer, but we see here a relationship with colorectal cancer, with malignant melanoma and birth weight. And also, very interestingly, increasingly seeing evidence that birth order can also influence later adult cancers, and not just hematopoietic cancers. So cancers such as melanoma, thyroid cancer, endometrial cancer. Some of this may be confounding by socioeconomic status, but still it's interesting to see the later influences of birth order on these cancers. And the most important element of looking beyond the I4C results is trying to understand the mechanisms for these associations. So some of the I4C related studies are already looking at epigenetics. So the epigenetics of birth weight, later on the epigenetics of leukemia, and now also a view towards the epigenetics of birth order. Hopefully, we will also have data on the genetic landscape of germline landscape of childhood cancer, and we'll be able to eventually do studies looking at gene-environment interaction. And speaking of the environment, this entire idea of the expososome, whether it's education, socioeconomic status, environmental chemicals, infections, lifestyle factors, all of these influencing both the mother, the intrauterine environment, and the child itself, influencing their gut microbiome or the development of their immune system. So the exciting elements of these findings, epidemiological findings in the I4C, hopefully will be able to be translated into more mechanistic data. And with that, I'd like to thank you all for listening. And I would like to give a special thanks to Gabriela Tikelis, who has done a remarkable job harmonizing and managing the I4C data, to our statisticians, Stan Lemachau and Gary Phillips, to Terry and Nikki for keeping it all together. Thank my co-authors and all working group members, and of course, all the participating cohorts, the mothers and their babies. Thank you very much.
It's a pleasure to talk to you today about our research on agricultural exposures in childhood cancer in the I4C. This is a two-part presentation. In part one, I'll be talking about parental occupational exposures to pesticides, animals, and organic dust. And in part two, my colleague, Dr. Rena Jones, will be speaking about proximity to agriculture. Agricultural exposures include pesticides, that is herbicides, insecticides, fungicides, as well as animal exposures and different types of organic dust. Parental occupational exposures to the child can occur during the pregnancy, as well as during childhood through exposures brought home on clothing and shoes. The general population living in agricultural areas can have exposure through the proximity of their homes to crops and animal operations, and that will be the topic of Dr. Jones's talk. So the I4C provided a unique opportunity to prospectively evaluate these exposures. But first, I want to share a little bit of background about these exposures in childhood cancer. Parental occupational exposure to pesticide has been consistently associated with increased risk of childhood leukemia. There's been fewer studies of CNS tumor, but these have also shown positive associations. In general, associations were stronger for mothers' exposures compared with fathers. And for the timing of exposure, the strongest evidence is for exposures during pregnancy. To date, almost all studies have been case control studies, and there are concerns about selection and recall bias. Parental occupational contact with farm animals has shown no association with childhood leukemia for mothers or fathers' exposures in a couple of studies. However, a recent Danish study found an inverse association for fathers' contact with animals and a risk of ALL in their offspring. Most studies of CNS or childhood brain tumors have shown positive associations with exposures to animals among either parent. Organic dust consists of dust of microbial, plant, or animal origin. And jobs that have particularly high exposure include farming, grain handling, carpentry, and construction. There have been few studies of organic dust per se in relation to childhood cancer, but some studies have focused on dusty jobs in the wood and textile industry. And these have shown that mothers' exposure increased risk of leukemia. And in one study, there was an increased risk of CNS tumors. For fathers' exposure, there's been mostly null findings for both leukemia and CNS cancers. This shows the 5 cohorts in the I4C that had complete occupational histories on mothers and fathers during the pregnancy. These cohorts were located in Norway, Denmark, the UK, Israel, and Australia. The Norwegian and Danish cohorts were the largest, with about 100,000 families enrolled, and they used similar protocols and questionnaires. In total, we had almost 400,000 live births. This table shows the I4C cohorts that were included in our pooled analysis of parental occupation. Cancer incidence was ascertained up through age 15. And for the Danish cohort, the DNBC, and the Norwegian cohort, MOBA, they provided 10% sample of their cohort as well as all childhood cancer cases. In total, we had about almost 600 childhood cancer cases that included 129 ALLs, 30 AMLs, and 158 central nervous system tumors that were mostly childhood brain tumors. We harmonized job codes from each cohort to the International Standard Classification of Occupation Code, and we linked those codes to the Aloha GEMS for organic dust and for pesticides. These job exposure matrices were developed by Hans Kromhout and Roel Vermeulen at Utrecht University. Animal exposures were identified by an NCI industrial hygienist, Dr. Melissa Friesen. The GEM combines intensity and probability of exposure, and there's 3 categories: none, low, and high. We had a fairly low prevalence of pesticide and animal exposure in these 5 cohorts, so we analyzed those as any versus none. We had a lot of information on potential confounders, including the mother's and father's age at the child's birth, education, smoking during the pregnancy, and for the child, we had information on birth order and birth weight and whether they were breastfed in the first 6 months of life. For missing covariate data, we used chain multiple imputation, and we estimated hazard ratios and 95% confidence intervals using Cox proportional hazard models. Final models were adjusted for child's gender and mother's and father's age at the time of birth. These analyses were conducted by a former postdoctoral fellow at NCI, Dr. Devin Patel, and they were published in the International Journal of Cancer early last year. This table shows exposure prevalence of mother and fathers. You can see that mother's exposure to pesticides in animals was too low to evaluate risk. We were able to evaluate all these exposures for fathers. Among fathers, pesticide and animal exposures were highly correlated. And about 85% of pesticide-exposed jobs were in agriculture. This slide shows the risk for leukemias with fathers' exposure to animals and pesticides. We saw an almost 4-fold increased risk of AML for fathers' occupational contact with animals, and about a 3-fold increased risk for pesticide exposures. We found no associations with these exposures and CNS tumors. This table shows mothers' and fathers' exposure to organic dust and risk of childhood leukemias and CNS tumors. Among mothers, we saw no association with organic dust exposure in relation to ALL, AML, or CNS tumors. The mothers' jobs were mostly low exposure jobs and were not in agriculture. For fathers, we saw a significant inverse association with ALL, with organic dust exposure, and a significantly increased risk of AML. There was no association with CNS tumors. We stratified fathers' exposure to organic dust by whether or not they had pesticide exposure on their job, and we evaluated risk of ALL and AML. You can see that we saw a similar association with ALL for fathers who had organic dust exposure, both with and without pesticide exposure on the job. And similarly for AML, we saw increased risk among fathers who had both jobs with organic dust exposure, both with and without pesticides, although risk was somewhat stronger for jobs that had both organic dust and pesticide exposure. We saw very similar findings when we stratified by animal exposure. The strengths of our study were that we had prospective data both on exposures and outcomes. We had complete occupational histories during the pregnancy for both mothers and fathers. And the use of a job exposure matrix allows evaluation of multiple exposures based on job title. Limitations were the low prevalence of exposure, especially among mothers, and the fact that particularly pesticides and animal exposures were highly correlated. Also, we had no information on parental occupational exposures after the child's birth. So in summary, we had novel findings. We found increased risk of AML with father's exposure to pesticides, animals, and organic dust. The association with organic dust was independent of pesticide and animal exposures. However, we could not identify specific agricultural exposures due to the high correlation between pesticides and animals and the limitations of the job exposure matrix. We observed an inverse association with ALL and father's organic dust exposure. And this is similar to a recent Danish study that saw an inverse association for ALL with father's exposure to animal dust. The possible mechanism to this may be related to early life exposure to infections that are known to decrease risk of ALL. In future work, we plan to expand these analyses to other I4C cohorts, and we will be able to use these harmonized job codes to evaluate other parental occupational exposures in the future. So I want to end my talk by acknowledging particularly my co-senior author, Leslie Stainer, the cohort PIs and investigators, and my colleagues at NCI and IARC. Thank you for your attention.
Thank you for joining me. I'm pleased to be presenting part 2 of this topic, where I'll be focused on residential proximity to agricultural exposures and childhood cancer risk. Dr. Ward provided some useful context on parental occupational exposure to pesticides and pesticide sources. The proximity of a home to crop fields increases pesticide exposure through pesticide drift through the environment, as well as take-home exposures. Increased crop density near the home has been associated both with increased pesticide concentrations in house dust, as well as with concentrations of pesticide metabolites. There are a few studies that have found increased risk of childhood cancers associated with crop density, although the literature is mixed on this topic. The evidence for associations with farm animal exposure is quite a bit more limited. There are some older studies that have found that contact with farm animals is associated with childhood brain tumors, and animal density near the home was associated with increased rates of childhood leukemia in a study of several US Midwestern states more recently. Denmark is an ideal setting for looking at the health impacts of these kinds of exposures because it's so agricultural. Over 60% of the land cover is agricultural, as you can see here in the yellow. And I've listed the major crops here on the left, cereals being the largest. Crops require pesticide application to protect them from weeds, insects, and fungus. Herbicides are the most commonly sold and used pesticide type in Denmark, and there are several that are used on large proportions of the crops, and those I've listed here. Animals are also a common commodity in Denmark. Pigs, cattle, chickens, and mink are the most common. And what I'm showing you here is changes in the numbers by decade, but trying to just give you a sense of the magnitude we're talking here in the millions of animals for chickens and pigs, for example. So a lot of animals. The aims of our study that I'll be presenting today were to investigate the association between crop area and farm animals near the home during pregnancy and subsequent risk of leukemia in offspring. This is recently published work, and I'll be presenting this work on behalf of Dr. Devin Patel, who was a former postdoctoral fellow at NCI leading this work under the direction of Dr. Mary Ward. You've heard by this point a bit about the Danish National Birth Cohort. This was conducted within the DNBC, this study of over 100,000 women and children from pregnancies from 1996 to 2003, and childhood cancer cases were ascertained through registry linkage. We had nearly 200 childhood cancer cases for this case cohort analysis. So we used the cancer cases and then drew a 10% random sample of non-cases and had roughly 9,000 children from singleton births without Down syndrome for our analysis of childhood leukemia and central nervous system tumors. The exposure assessment started by geocoding all addresses during pregnancy. This was previously done. And we calculated the land area coverage of major crops within buffers around the home. And so we did that at a range of distances from 100 meters out to 1,000 meters. I've depicted here a 500 meter and 1,000 meter buffer to show you how we did that. So within the buffer, we simply estimate the proportion of the area in this circle that is of a particular type of crop. So here we have a little bit of peas and a little bit of spring cereal in the 500-meter buffer. And when we go out to 1,000 meters, you can see the area of spring cereal gets larger, as does peas. And now we've got potato crop and maize crop. We did the same thing with animal counts and estimated nitrogen excretion from those animal counts within the buffers. That was a simple computation of the number of animals by specific type multiplied by their specific nitrogen excretion rates. And that's because nitrogen is the major waste product, major compound of the waste that's coming from animals. So this gives us an indication of the relative volume of nitrogen coming from different animal types. I'll be presenting the results from our analysis only at the 500-meter buffer for simplicity today, and also because that is a distance for which associations between crops and pesticide exposures have been linked in previous literature. We did Cox proportional hazards analyses to compute hazard ratios for risk in their confidence intervals, and compared both crop and animal exposures to common reference groups where people did not have those exposures within the buffer. So crop area, we compared high and low crop area, defined as the median split, within that 500 meters compared to people with no crops within 500 meters, and likewise animal next values split at the median compared to people who had no animal exposures within 500 meters. All of the models adjusted for maternal age and child's gender, and we mutually adjusted crop and animal models, and I'll show you the impact of that coming up. This gives you a feel for the densities of some of the common crops in Denmark geographically. And you can see there are clear geographic patterns. They're not equally distributed across the country. Winter cereal is the most common crop, and you can see that the strongest or highest densities rather are here in the red. And grass and clover, for example, has a very different distribution where it's more concentrated in the Southwest, for example. Animal densities likewise have their own distributions. And here we've got cattle, and to the right, pigs, which as you can see from the maps look pretty different. And interestingly, if I swap out this pig map with the grass and clover map, you can see just visually how clear that correlation is between where the cattle are raised and where the grass and clover they graze on is grown. When we looked at the distribution of crop acreage within the DNBC cohort, over 60% of the population had at least some crops grown within 500 meters of the home. Again, the most common grown near the home was winter cereal. No surprise, it's the most commonly grown crop in the country. And the median crop area was 14 hectares. And as you can imagine, there were moderate correlations between the types of crops. So cereals tended to be grown near each other. And so people tended to have exposure to both within 500 meters. The association between childhood leukemia and total crop area within the home is presented here. And you can see we saw an increased risk of about 1.9 hazard ratio for above the median level of crop area within 500 meters of the home and childhood leukemia. When we broke that out by major crop types, we could see some variation by crop types. It was a little hard to evaluate trends here with some of these small numbers, but you can see associations with winter cereals, grass and clover, peas and maize here, and these are in models not adjusted for animals. And when we adjusted for animal next, we saw this interesting pattern where, although confidence intervals certainly overlapped, the effect estimates tended to strengthen. So that indicated, a need to look at the independent effect of animals on these associations. We did not see associations between crop area and CNS tumors, at least nothing that achieved statistical significance, although there were some elevated point estimates. When we looked at animals within 500 meters of the home, we saw no real associations with childhood leukemia, whether or not we adjusted for crops. But we did see an association between cattle density and CNS tumors. And you can see here that that was robust to adjustment for crops around the home. So because we saw these associations with crops around the home, the obvious question is that driven by pesticide exposure? And as it turns out, this is a little hard to evaluate with the data in Denmark because there are only sales data available during the period of the DNBC. So there are application rate data available more recently, And so our agronomist collaborator, Steen Gillenhern, used the application rate data from more recent data and adjusted the historical sales data to come up with an estimated application rate for herbicides around the home to the crops that were near the home. We limited this analysis to active ingredients that were used on 20% or more of the area of major crops around the home, and a lot of pesticides were used on multiple crop types. So the analysis certainly has some limitations. And what we saw were positive but non-statistically significant associations for childhood leukemia and none for central nervous system tumors. This was associated with 3 pesticides and 1 fungicide in particular. So overall, we saw an increased risk of childhood leukemia associated with total crop area and specific crop types. And in these limited analyses, application of specific pesticide active ingredients, rather. And we did see an increased risk of CNS tumors associated with high density of cattle near the home. Again, these findings are consistent with that small body of literature that I started this talk talking about, but those were mostly of ecologic design. And in this study, we had measurements at an individual residence level. We also had a complete residential history during pregnancy, so we were able to apportion exposures to each of the homes they spent their time during that pregnancy period. And of course, this was a prospective study, so it has those advantages. There were limited sample size, fewer than 200 childhood cancer cases. The animal data are reported annually, and we have no information on home or garden use of pesticides, which could certainly confound some of these associations. And as I alluded to, the pesticide application data are limited. We plan to follow this up in a couple of ways. There are potential additional analyses in the DNBC where we could expand to other pesticide types that are used very commonly and look at trimester-specific exposures. We're evaluating the feasibility of replicating this in some form in MOBA and planning to follow up using in a nationwide study in Denmark using a record linkage approach. So I just want to acknowledge all the co-authors on the paper, and many thanks for your attention.
Hi, and thank you to Terry Dwyer for inviting me to speak to the I4C virtual annual meeting. The title of my talk is Cancer Progress and Priorities, Childhood Cancer. And that is also the name of a position paper published last year by Dr. Philip Lupo of Baylor and myself in Cancer Epidemiology, Biomarkers, and Prevention. And the intention of this paper was really to mark the passing of the torch from me to Philip. I am the immediate past chair for epidemiology with the Children's Oncology Group, a position which Philip now holds. And we did not pretend to be doing a systematic review of the state of childhood cancer epidemiology, but rather it's our impressionistic views of the field, what we've accomplished and what we need to do, especially in order to understand the causes of childhood cancer. So this talk is really a brief of the position paper that we published. And I should add that any graphics that you see come from the paper, or if not, then we can let you know where they come from in the slide. So, of course, we all know that incidence of childhood cancer varies by geography, and actually because we have numerous examples of immigration and diaspora populations by people. But I have come recently to appreciate that incidence is not the best measure of the burden of childhood cancer. Rather, that would be disability adjusted life years, which of course are a combination of incidence, survival, and prevalence, as well as of the degree of dysfunction that occurs in survivors. And viewed this way, you can see that the largest burden of childhood cancer is in South Asia, Southeast and East Asia, Sub-Saharan Africa, and North Africa and the Middle East, which is in pretty sharp contrast to where the epidemiology is. So although I'll end with this note, I'll just say that one clear message that Philip and I made was that childhood cancer etiologic research absolutely needs to shift to the developing world in order to make sure that the largest number of children impacted by cancer are getting studied. Of course, we know that the descriptive epidemiology of childhood cancer is very interesting, with a distinct early life peak that it comes from mainly from childhood ALL, a nadir at 8 to 9 years of age, and increasing incidence up till 19, and of course continuing all the way through adulthood. But there are still other lessons to be learned from descriptive epidemiology. So for instance, in the recent past, my group has published on the sex ratio by single year of age in childhood cancer. And there are some very interesting leads to be followed. For instance, in Hodgkin lymphoma, the incidence ratio for males compared to females is quite wide in early childhood and sinks to next to nothing in late teen years. And surely something is there to be gleaned from that. And for that matter, while there are well-known differences in incidence, for instance, between children of European and children of primarily African descent, there are other differences that seem very interesting that haven't been appreciated until recently. So last year we published, again from my group, a SEER analysis which demonstrated, for instance, that compared to non-Hispanic white children, Southeast Asian children had about 2/3 the risk of ALL. And in looking at AML, children from Oceania, meaning Pacific Islanders, had a 4-fold risk of AML compared to non-Hispanic white children. And there are surely more such patterns of incidence to be discovered. We just need to go looking. Also, we have a international database, the childhood incidence on 5 continents, cancer incidence on 5 continents, as well as many other sources of data, which are allowing us to take a look at trends over time, which themselves are very informative. And so again, from my group, a couple of years ago, we published on trends in cancer incidence from 1988 to 2012 in the CI5 data, and demonstrated that hepatoblastoma is the childhood cancer under 5 with the fastest rising incidence, and this was true in most regions of the world. Clearly, this indicates that there must be a environmental factor or a lifestyle factor that is changing in most areas of the globe, which limits the possible factors to just a few. So descriptive epidemiology is very useful for generating hypotheses. Of course, we're in the business of analytic epidemiology. And as you well know, there has been, at this point, nearly 40 or 50 years worth, which has started to be synthesized in meta-analyses as well as pooling projects, such as the Childhood Cancer and Leukemia International Consortium and I4C. And so we do have a good idea for those tumors where there have been sufficient studies. We have what I would call an evidence of absence or evidence of presence of risk factors. And for the less common tumors or less studied factors, we may still be in the realm of absence of evidence. But in general, we can divide our risk factors into the gestational and perinatal risk factors, which are pretty robustly examined at this point. And then environmental risk factors or behavioral risk factors, which are somewhat more difficult to establish for reasons that most epidemiologists would recognize. Nevertheless, out of this data, we do have some exposures or characteristics that are very robustly associated with pediatric cancer. Some of them are, at this point, quite prosaic, let's say birth weight or parental age. Nevertheless, because there's such strong and robust clues to etiology, we should be trying to elaborate why exactly it is, for instance, that children of older parents have a higher risk of cancer. Other risk factors, such as breastfeeding, it certainly would be good to understand why breastfeeding prevents many childhood cancers, although it is also a good in and of itself, and we can begin to suggest that that prevention of childhood cancer is yet another reason to be breastfeeding. Where do we go from here? We may be at the limit of questionnaire or geographic-based analyses of childhood cancer risk from the environment. And I would suggest that we need to move to molecular assessment of exposure, for instance, DNA methylation. In case control studies, that will mainly be in newborn dried blood spots, which it only tells us about one point in time. I think the I4C has a very big role to play in looking at methylation over time in children, which hasn't been looked at all, and really can't be in case control studies. We also need to bring in tumor data, not just to look at individual subtypes, but to look at mutational signatures, which, as many of you will know, are the remnants or tells of exposure that are present in the tumors, and many of which appear repeatedly in cancers but don't have a definitive cause. Nevertheless, in pediatric cancer, especially because our tumors are fairly mutationally silent, we may have a better shot at being able to link a exposure and cause for these signatures. Of course, you're all aware that in pediatric cancer, there have been now numerous sequencing studies which have established the presence of high penetrance pathogenic variation in pediatric cancer, but it accounts for only a minority of cases, depending on the type of cancer. But for ALL, for instance, it's well under 10%. By contrast, common variation, meaning SNPs, is far more strongly associated with pediatric cancer than in adults. And so this has been done repeatedly for ALL, both B and T cell, Ewing sarcoma, and neuroblastoma, with which now have a pretty mature genetic epidemiology. Smaller studies or single studies have looked at Langerhans cell histiocytosis, osteosarcoma, and Wilms tumor. And so we look forward to more such studies, but honestly, there are other study designs that we need to be considering. I meant to add that the common genetics is adds up to actually a very wide range in risk. So comparing the lower end of the distribution to the upper end in ALL gives you a 10-fold difference in risk. So when I say other means of analysis, for instance, because we know there are persistent differences in incidence between people whose ancestries originated on different continents, we can use that information when there's a genetic admixture. And so, for instance, in South America or Latin America or among African Americans, there's a detectable admixture, meaning that different segments of the genome can be attributed to different ancestries, and we can use that information to isolate genes that explain the difference in incidence between continental ancestries. I want to add that GWAS only works within an ancestry when there is variation at a locus. But for loci that are fixed in a population, the only way we could discover its association with cancer is by admixture mapping. We also should be pursuing transcriptome-wide association studies, which have been employed to great effect in adults. The major roadblock here is that most of the information that would go into an integrative analysis like this comes from adults. And of course, we know that children are not little adults, and also that childhood cancer develops in utero in many cases. And so we are lacking sources of integrative data that come from the proper stage of life, and these need to be developed. So I will end by saying that we need to take much more of a global approach. CLIC and I4C are already doing that, albeit mainly in developed countries and mainly with European or East Asian descent children. We need to be cultivating childhood cancer etiologic research in other regions of the world where the burden is highest, as well as to be studying the genomes of children that reflect the diversity of children worldwide. So with that, I am happy to take your questions. Obviously, I can't take them right now, but feel free to email me at spector@umn.edu. And thank you very much for listening.
Good morning, good afternoon. I would like to thank you for being with us here, to thank the organizing committee for inviting me to join you today with discussing the approach we took in identifying the cumulative evidence on exposure of pesticides in childhood leukemia risk, appraising and synthesizing it. Before starting our discussion, I would like to remind you how far we've come regarding the assessment of pesticide exposure and its link to child health through the years. So there has been significant progress regarding and given the many challenges in the field, we have identified specific associations that seem to be robust and of course, we have a long way forward into identifying any other associations that have been postulated in the past. So another introductory slide and a final thought on the general background of this work. So any health situation that we need to be aware of, including, of course, childhood leukemia, needs to be taken and put into a surveillance system. And that system is quite complex, not only in terms of the various tools that can be used to address the question under study, but also to the various disciplines, scientific disciplines that are involved and can be helpful in identifying these associations and, of course, incorporating this information into policy making. The objectives of the present work were to systematically retrieve and appraise the accumulated epidemiological evidence on the associations between exposure to pesticides and childhood leukemia. And the methods we used were the retrieval and assessment of case control or cohort studies, where any type of pesticide exposure was assessed and was related to childhood acute leukemia. The summary effect estimate that we used was the odds ratio and its 95% confidence interval, and we implemented a random effects meta-analysis model, as well as subgroup and sensitivity analysis pertaining to the type of exposure, the exposed populations, and the windows of exposure. So if we look through the available data, we started off with 200,000 citations, and through the various screening steps, we ended up with 52 publications, 52 studies, which corresponded to more than 160,000 participants across 30 different countries. So this was something encouraging to start with. The evidence base, the index evidence base is quite large, and indeed the study characteristics are here. 90% of the eligible studies were case control studies, accumulating 34,000 cases and more than 120,000 controls. And also 5 cohort studies were included, pertaining to 938 incident cases and more than 7 million total participants. The Americas accounted for more than 40% of the included studies, 30% came from Europe, 20% from Asia, and we had 4 multi-center studies, including the CLIC and I4C Consortium. The study quality, although it was not very frequently high, only 6% of the studies were characterized by high quality. It was not of low quality, though 94% of the studies were intermediate quality. And the main reasons to downgrade from high quality to intermediate quality were the partial exposure assessment and the non-specific exposure assessment. So how does this compare to what is known in the literature? This is an overview that we had done across any epidemiological study that assessed pesticide exposure in the field. And this is a helpful information about the specific, the assessment of specific types of exposure in the field. So what it seems is, what is prominent here is that the literature along the way has not changed its pattern of targeting specific compounds. So the number of studies that try to address specific compound association has not changed really after time. And as I will explain further on, this has not changed for the occupational pesticide exposure. If we go to the outcomes now and the outcome assessment and the outcome ascertainment, we can see that these are all the associations that are included in the cumulative literature, in the published literature for pesticide exposure in human health. We see that child health is indeed an important part of this literature, and cancer is an important part of this literature. So childhood cancer plays a prominent role, holds a prominent place in the literature regarding the associations between pesticide exposure and human disease. So going back to the risk of bias, having had a glimpse on the available evidence, we see these are data coming from the literature on adult. This is AML, adult AML cases. Here, if we go to the exposure assessment, we see here that the same situation is present for the literature not related to children. And we need to also keep in mind, while we're discussing this, that exposure, indirect and direct methods of exposure can be merged, can be combined to provide information about exposure models, which today is very, very helpful. So into our database, the exposure assessment was done in the majority of the studies in an indirect way. So we have a self-reported exposure assessment in 50 studies. The biomarkers were used in 2 studies, biomarkers in urine and bone marrow, and external exposure assessment in dust was used in 2 studies as well. Exposure codification was very rare. In most of the studies, we had the comparison between any versus never exposed to pesticide, the frequency of exposure and the duration of exposure. Their characterization was very, very poor. And regarding the windows of exposure, obviously we had the 3 windows of exposure, the preconception, pregnancy, childhood window. Does this compare to what's happening to the remaining literature? The answer is yes. Indirect exposure, this comes from a systematic review assessing the exposure assessment in epidemiological studies on occupational exposure to pesticides. 78% used an indirect exposure assessment framework, including self-reported exposures and job titles. And what's interesting is that most of the case control studies use indirect exposure assessment, and most of the studies coming from high-income countries use actually indirect exposure assessment. And this can be explained by the fact that these countries have the capacity to perform either longitudinal studies where they can address this issue retrospectively or prospectively. So a direct exposure assessment was present in the literature of the adults of the occupational exposure in 21% using biomolecular blood and urine. Cross-sectional studies, usually in 30% of these efforts, the studies were cross-sectional in design, and also in 41 of these studies, the countries involved were lower to middle income countries. And this can also be explained using the opposite argument as used for the indirect exposure assessment, that these countries do not have the capacity to perform longitudinal studies, so they use direct exposure assessment and cross-sectional study design. So there was no change in the trend ratio for indirect to direct methods of exposure assessment. In our database now, for the exposure during preconception, we identified 70 studies pertaining to 112 associations. However, when we tried to define a clear research question, the number of studies involved was very small. We only had 2 studies assessing the association between maternal and environmental exposure and acute leukemia, and another 2 studies assessing the maternal occupational or mixed exposure and ALL in our database. Click studies were there, finding statistically significant associations for environmental exposure in insecticides, herbicides, and rodenticides, and also for parental occupational exposure and B-cell ALL in these databases. Exposure during pregnancy, another very interesting window of exposure, 26 studies here, 218 associations. Of these, 41 statistically significant overall. When we try to zoom into the data, there indeed we had the evidence coming from the large studies, showing some of them showing statistically significant results as the CLIC consortium, and some of them showing non-statistically significant results. And when do we try to synthesize the evidence? Again, the number of studies, if we think about the large number of studies where we came from, are small. So we only have 6 studies assessing the association between maternal environmental exposure and acute leukemia, yielding a statistically significant result. And we have only 3 studies assessing the association between maternal environmental exposure and ALL, again yielding a statistically significant results. Statistically significant results were also observed for the association between environmental exposure to herbicides and environmental exposure and insecticides. This is the forest plot for this particular association as I described it, and we can see that the heterogeneity of the studies reaches 51.3% at the I-square. Infant leukemia, this is a quite interesting research question, very small number of studies. However, the associations we have are statistically significant, and here we need to dedicate a lot of time and effort into delineating the nature of these associations in more detail. Exposure during childhood, 29 studies, 5 of them in infancy, 118 association, yet only 5 studies assessed any type of pesticide exposure in acute leukemia, and only 2 studies assessed insecticides in ALL, both yielding a statistically significant result. And here again, a forest plot showing the results of the meta-analysis with a high, the presence of high heterogeneity reaching an 8%. If we try to compare these to other fields, we see here that the results are comparable in terms of the effect direction and the effect magnitude. And if we go one step further and try to identify the leukemia pathways, sometimes a pathway may seem simple. So we have several steps, a linear progression of the pathophysiology, so to say. However, we need to take into consideration that usually pathways are much more complex. So we have many levels of interaction for the biological pathways and a distinct field of research which should be dedicated to delineating these results. Just a few thoughts about the European perspective and the use of epidemiological studies in risk assessment and in decision making. Childhood leukemia is one of the case examples where the European Union, the European EFSA has a lot of activity on trying to link epidemiological studies, their result, and animal data, and creating an adverse outcome pathway framework. Finalizing my thoughts and my presentation, I would like to say that if we need to put this data into context, we need to link the research synthesis efforts with the primary research study and actually the question that has been put forward. Is this about safety? Is this about toxicity, efficacy of interventions that lower pesticide exposure? Is it about pathogenicity and so on and so forth? Epidemiological studies have a lot to offer to all these questions, and it is important that we understand that hazard identification should ideally lead to risk characterization, the quantification of the association under study, and that exposure assessment should include the duration, the intensity, compound-specific and geographical variation in order to be able to translate the findings of these studies into policy. Better phenotyping is a thing that we discuss a lot, leukemia subtypes, molecular characterization, and of course, infant leukemia versus child leukemia is a huge area of research that also needs to be argued and discussed in detail. All these need to be complemented by functional studies, by animal data, by studies that would support the mode of action and actually will be able to create and contribute to the robustness of the associations on the study. And with this, I would like to thank you. This is a foggy picture coming from our city of Ioannina here at the University of Ioannina. We all do believe that this is going to be translated into an association that would read a productive phase, even though technology triggers such as new associations or new compounds first are characterized by high expectations, then by a phase of disillusionment in order to be able to reach this productivity plateau, as I explained. And these are all the people that had dedicated time, effort, and intelligence to fulfill this project and discuss this with you. Thank you very much.
Thank you for having me. Today, I'm pleased to present about trends in pediatric central nervous system tumor incidence in the United States from 1998 to 2013. I'm currently at Oxford, but this work was conducted at the US National Cancer Institute, and the results can be found in this publication in Cancer Epidemiology, Biomarkers, and Prevention. In my talk today, I'd like to talk about why pediatric CNS cancer trends are important, what the gap is in the literature, how we studied the trends, what we found, what might explain the findings that we had, and some future directions. So beginning with why are pediatric CNS cancer trends important? As many of you will know, cancer is the second leading cause of death in childhood, and CNS tumors are the leading cause of childhood cancer deaths. The etiology of pediatric CNS tumors is largely unknown. Genetic predisposition syndromes, ionizing radiation, and high birth weight are known risk factors for pediatric CNS cancers, but they account for a small percentage of cases. Radiofrequency electromagnetic fields are non-ionizing and haven't been definitively associated with cancer. But because children are especially sensitive to cranial radiation, there's concern that rising radiofrequency electromagnetic field exposure may result in increasing incidence of pediatric CNS cancers. Given our limited understanding of CNS tumor etiology, monitoring trends can provide insight and drive hypotheses. There is literature about the descriptive epidemiology of childhood CNS tumors, but this doesn't typically focus on trends specifically. And when it doesn't focus on trends specifically, there's limited discussion of the methodological challenges and the difficulties in interpretation of these trends. Furthermore, generally the trends are measured using high-level categories, and they aggregate many subtypes, which may have different etiologic patterns. Reporting on all CNS cancers combined can mask important subtype-specific changes over time, whereas other studies which report on a single subtype alone may be misleading due to the heterogeneity of CNS cancers and potential shifts in diagnosis and reporting from one subtype to the other. So we aimed to provide a comprehensive overview of recent incidence rates and trends for the most common histologic subtypes of pediatric malignant CNS tumors and pilocytic astrocytomas. Pilocytic astrocytomas are not considered malignant, but have been collected routinely in registries since before the Benign Brain Tumors Act of 2004. To conduct this analysis, we used 29 registries from the North American Association of Central Cancer Registries that had received gold or silver certification for at least 14 of the 15 years that span 1998 to 2013. These registries cover approximately 60% of the US population. As I mentioned, we included malignant CNS tumors and pilocytic astrocytomas diagnosed in persons 0 to 19 years old. We excluded germ cell tumors, neuroblastoma, and lymphomas. When considering how to classify the tumors, we identified several options: the International Classification of Childhood Cancers, the WHO Classification of CNS Tumors, and the Central Brain Tumor Registry of the US Classification Scheme. Looking at the ICCC3, this was designed for all childhood tumors to agree with current international standards, to integrate entities defined by newly developed diagnostic techniques, and to ensure continuity with previous childhood cancer classifications. But for CNS cancer specifically, the categories tended to be either too narrow or too broad to conduct meaningful trends analyses, and our clinical collaborators found that they had insufficient clinical relevance. An alternative scheme was the WHO classification scheme for CNS tumors. This was designed for all CNS tumors, but was not specific to the pediatric setting. And it's regularly updated to reflect advancements in diagnosis and prognosis, which make it inappropriate for trends given the changing schemes over time. We ended up choosing a modified version of the Central Brain Tumor Registry of the US scheme. The downside is that this is not necessarily compatible with the international standards. The advantage is that it provided fine categorizations that were clinically relevant. We stratified malignant tumors into those that were classified as gliomas, embryonal tumors, ependymal tumors, and other. We further stratified gliomas into those that were considered high-grade, low-grade, and other. And embryonal tumors were classified as medulloblastoma, PNET, which is pediatric neuroectodermal tumors, or other. For our analysis, we estimated age-standardized incidence rates standardized to the 2000 US standard population, and we expressed rates per million person years. We estimated annual percent change, which has been reported as a summary measure without inflection points to provide an interpretable summary and prevent overinterpretation of potentially unstable estimates at the tails. Annual rates of each subtype by age have been displayed graphically so that you may make interpretations based on the shape of these curves. We also estimated the absolute change in the number of cases diagnosed annually by taking the difference in the number of cases estimated based on modeled 2013 and 1998 rates applied to the 2013 US population counts. We stratified incidence rates by age, sex, and race ethnicity, and further stratified gliomas by topography and specific histologic subtype. We stratified gliomas and pilocytic astrocytomas by method of diagnostic confirmation. What did we find? We included about 18,612 malignant cancers and 6,856 pilocytic astrocytomas. You can see that these tumors were distributed by age. They were slightly more common among males, and that between 60 and 70% of tumors were diagnosed among non-Hispanic whites. I want to use this graph to introduce you to the graph that I'll be showing in the future. So here you can see that risk is slightly more common among males. These dashed lines represent no significant change over the time period in rates. A solid line indicates a statistically significant increase in the rates, whereas a dotted line will indicate a statistically significant decrease. You can see here that for all pediatric CNS tumors, the rates by age group remained stable over the time period. When we look at pilocytic astrocytoma, the rates were also stable except for among those 15 to 19 years of age, where we saw a slight increase. When we look at the major subtypes of malignant tumors, we see that gliomas are the most common and account for 57% of all malignant tumors. The incidence rates of glioma increased by 0.77% per year. These increases appear to be consistent across age, sex, and race. In this next graph, you could see that the rates of other glioma increased significantly, while the rates of low-grade gliomas decreased significantly. When we look specifically at the embryonal tumors, we see that overall there was a decrease in the incidence of embryonal tumors. These accounted for 29% of all malignant CNS tumors. We see stable rates of medulloblastoma, decreases in pediatric neuroectodermal tumors, and significant increases in other embryonal tumors. This category of other embryonal tumors includes the atypical teratoid or rhabdoid tumors, which were newly introduced as a category within this time period. When we stratify the results by subtype and age, we find that the patterns by age group are not highly distinct from those for all ages combined. One thing to note is the embryonal cancers are more common in the 0 to 4-year-olds, especially the ATRT, which is shown in the bottom line in brown and was not sufficiently common in the older age groups to make a trend line. When we look at the gliomas by topography and histology, here on the left by topography, we see statistically significant increases in tumors of the brainstem, optic nerve, and frontal lobe. And while the notation has changed slightly here and I have a solid line, statistically significant decreases in gliomas found in the parietal lobe. When we look at specific histologies, we see statistically significant increases in glioma malignant, pleomorphic xanthoastrocytoma, and glioblastoma NOS, whereas we see statistically significant decreases in oligodendroglioma, fibrillary astrocytoma, and astrocytoma NOS. When we look at the rates by method of detection, we can see that in red, the microscopically confirmed rates are remaining relatively stable. For malignant glioma, the radiographically confirmed cases are increasing and make up quite a large proportion of the overall rates. For pilocytic astrocytoma, we also see a very modest increase in the rate of radiographic confirmation, although they make up a much smaller proportion of the tumors. To summarize, we found that all malignant CNS cancer incidence did not change, but glioma incidence increased by 0.77% per year, which would amount to 120 additional gliomas diagnosed in 2013 than would be expected based on 1998 rates. Embryonal cancer incidence rates decreased by 0.88% per year, which would result in 72 fewer embryonal cancers diagnosed. And finally, pilocytic astrocytoma incidence increased by 0.89% per year, which would amount to 94 additional pilocytic astrocytomas being diagnosed in 2013. By including more narrowly defined histologic subgroups, we've shown the diverging patterns in the subtype-specific incidence rates underlying a higher level average trend. What might explain these findings? One of the things that might lead to changes in the trends over time is changes in molecular pathology. For example, up until the late 1990s, PNET and ATRT were difficult to distinguish based on clinical and pathologic features, and most tumors were classified as PNET. Since then, increasing recognition of the distinct genetic signature of ATRT has increased the frequency of its diagnosis. A similar case occurred with astrocytoma NOS, whereas now those who have an H3F3A mutation are classified as glioma NOS. Furthermore, increases in diagnoses occurring by imaging, such as those we saw for the gliomas, could result in increased reporting of less specific histologies. Over time, these radiographically diagnosed tumors may be seen more frequently by radiologists without intervention, and so there might be increased reporting by radiologists. And lastly, the increases in the technology for imaging may have led to the detection of not previously detectable cancers. It's also possible that these trends relate to differences in the risk factor prevalence. We saw a steeply increasing use of CT scans over time, but gliomas, which showed an increase, are not the most radiogenic tumors, and so it's unlikely that this accounts for the difference in gliomas. Furthermore, we would only expect to see an increase due to ionizing radiation in those aged 5 and older, due to the latency associated with exposure to radiation. The as low as reasonably achievable principle has been implemented in hospitals in the 2000s and may lead to a reduction in exposure to ionizing radiation. The risks associated with non-ionizing radiation remain unclear, and high birth weight has been declining in the US, and so this wouldn't account for the increases in certain subtypes that we saw. One of the limitations of this study is that it's hard to disentangle true changes from changes in classification, diagnosing, and reporting. But some of the strengths are the high coverage, 60% of the US population. The size of this study led us to be able to examine the rates of relatively rare tumors, and the quality of the data, which means that the rates are reliable. In the future, large biobanking efforts may allow for the retrospective classification of tumors using standards that reflect present or future understanding of etiology. Furthermore, the development and promotion of a historically compatible, clinically relevant, and highly acceptable classification scheme for pediatric CNS tumors will improve the future feasibility, comparability, and usefulness of trends analyses. Finally, continued surveillance of pediatric CNS tumors should remain a priority given their significant contribution to pediatric cancer deaths. I would like to thank my co-authors, and I've included my email here in case anyone would like to contact me. Thank you.
In this talk, I'll start with a brief look at recent results on incidence trends for all childhood cancers combined, and then move on to more detailed consideration of a few specific cancers of particular interest. For reasons of time, and because they've already been covered in another presentation, these will not include brain tumours. This first slide shows incidence rates by world region in the 1980s and 20 years later from the IARC project, International Incidence of Childhood Cancer. There were increases of varying magnitude in all regions except sub-Saharan Africa. The data were all taken from population-based cancer registries and were standardized and reviewed using similar methods, but geographical coverage within each region differed between the two periods. This was especially marked in sub-Saharan Africa, and therefore one should not attach too much importance to the apparent decrease there. By contrast, another IARC project, the Automated Childhood Cancer Information System, this time covering Europe, used data from the same cancer registries throughout the study period. As shown in this slide, for children aged under 15 years, incidence rose at a little over 0.5% per year for all cancers combined. And there were fairly similar patterns in 4 geographical regions of Europe. For teenagers aged 15 to 19 years, now frequently included in the definition of childhood for epidemiological studies, the increase was steeper, about 1% per year. In Japan, however, over a similar period, there was a substantial decrease in childhood cancer incidence. Here, compared with the more modest increase observed in England, which was typical of European countries. The reasons for this will be discussed a little later in the talk. It is well known that some of the highest rates of acute lymphoblastic leukemia, the most common of all childhood cancers, occur in Hispanic populations of the Americas. This slide shows that in the United States, in the early 1990s, incidence of ALL was already 1/3 higher in Hispanic whites than in non-Hispanic whites. Between then and 2013, incidence rose faster in Hispanic whites than in any other ethnic group, at about 1% per year. The very slight increasing trends for the other 3 main population groups were all non-significant. In the Netherlands, over a similar period, for the whole of childhood combined, in this case up to the 18th birthday, there was a borderline significant increase in the incidence of ALL. No individual age group had a significant increase, but the steepest increases appeared to be in the older children. This may have been related to the fact that over the study period there was an increase in the referral of older children with leukemia to pediatric oncology units. In Saudi Arabia, recorded incidence of ALL rose steeply between 2001 and 2014, by which time they had reached a level fairly similar to that in the United States. This increase was thought likely by the authors of the study to reflect improved diagnosis and improvements in reporting to the cancer registry, but also perhaps socio-economic development over the study period was a factor. Neuroblastoma is the only childhood cancer for which population screening has ever been feasible. In Japan, a mass screening program for neuroblastoma in infants was halted in 2003 because it had become increasingly obvious that it had led to massive overdiagnosis of asymptomatic cases that would be expected to regress spontaneously. After the screening programs stopped, there was a dramatic decrease in the incidence of neuroblastoma in the first year of life in Japan. In fact, to below the level seen even in England without systematic screening. And this decrease was large enough to account for the decrease in total childhood cancer incidence in Japan shown earlier. Following the end of screening, there was little evidence of any increase in mortality from neuroblastoma. The lower incidence has persisted, though with maybe a hint of a slight increase in the 1 to 4 year old age group. Childhood liver cancer incidence showed strikingly similar increases in Canada, the United States, and Australia over a period of almost 30 years, starting in the mid-1980s. In these and other Western countries, liver cancer in children is mostly hepatoblastoma, occurring predominantly in early childhood. And low birth weight has been repeatedly found to be a risk factor for hepatoblastoma. It seems likely that some of the increase in hepatoblastoma incidence is due to increase in the number and survival of low birth weight babies, though any underlying mechanism remains obscure. When analysis is restricted to hepatoblastoma, a similar pattern emerges, not only in North America, but also in Europe and, as shown here, in Taiwan. However, this forest plot overstates the tightness of the confidence interval for the overall rate of change. That is because of the extensive overlap of data between the 4 American studies with effective double, triple, and even quadruple counting. But even if it had been possible to produce a single unified US data set for this study, or if merely the largest US study had been included and the others dropped, there would still clearly have been an overall increase in hepatoblastoma incidence of much the same magnitude. In populations where hepatitis B is endemic, hepatocellular carcinoma has been the dominant childhood liver cancer. In Taiwan, which pioneered universal vaccination of infants against hepatitis B, the incidence of liver carcinoma has fallen to well below half of its former level among children, and subsequently this decrease has fed through to older age groups. This next slide shows some of the results of the data in the most recent volume of International Incidence of Child Cancer for thyroid carcinoma. The incidence of thyroid cancer in older children has increased in many populations worldwide. As in older age groups, where of course the incidence is higher, this seems to be largely, though not entirely, due to increased detection of asymptomatic thyroid nodules, some of which harbour asymptomatic thyroid carcinomas. The striking exception to the pattern of increase is the large decrease in Belarus. This is easily explained by the second period, 2008 onwards. Everyone in that country who had been alive at the time of Chernobyl had passed the age of 20 years, and therefore the Chernobyl-induced increase in thyroid cancer incidence had disappeared. Malignant melanoma in Australian children has been decreasing since the early 1990s. Whereas in England, where it is admittedly much rarer, rates have remained constant. In adolescents and young adults in Australia, the decrease began later, especially in males. In females, it began in the mid-1990s and about 7 years later in males. In England, however, where there has been no vigorous Australian-style public health campaign against excessive ultraviolet exposure, rates have risen by 2010 almost to Australian levels. In the Netherlands, again, there were constant low rates of melanoma in young children, but an increase in teenagers until around 2005, which was then followed by a steeper decrease. This has been matched by a very similar pattern in the United States. So, to summarise, the causes for a few trends in incidence of childhood cancer are at least moderately certain. These include changes in diagnostic practice for thyroid cancer, the abandonment of screening for neuroblastoma in Japan, the passing of the excess risk of thyroid cancer in Belarus, as in Ukraine and parts of Russia, reduction in UV exposure leading to decreases in malignant melanoma in several countries, and the success of the hepatitis B vaccination programs in countries where that disease has been endemic. Originally in Taiwan, but now in many other countries. And no doubt, in many countries, changes in cancer registry sources of data and in the efficiency of operation of registries, and perhaps even in their coding practices, will have led to trends in the recorded incidence. But mostly, the causes of changes in childhood cancer incidence remain unknown, as do the causes of these cancers themselves. But we must hope that some will be revealed by current cohort studies.
Good morning, everybody. My name is Lorenzo Ricciardi. I'm from the University of Turin in Italy, and I will talk about causal inference methods in life course epidemiology. And I would like to thank the organizer of the I4C Annual Webinar for the invitation. My talk will be a methodological talk, and will first introduce the concept of causal inference applied to life course epidemiology, and then elaborate a bit on a couple of applied examples. So, in essence, causal inference implies first formulating causal questions. For example, we could use a potential outcome framework and ask questions like, what would happen to the probability of the outcome had the exposure been set to the level A equal A or A equal A star, where A and A star are the two potential outcomes. Once we have formulated the causal question, we have to define the estimand and choose the estimation approach. And it is really important that we are being transparent about the underlying assumption of the chosen estimation approach. So to broaden the picture, causal inference is strengthened by integrating and putting together different pieces of evidence. And I'm referring here to two quite recent, relatively recent papers. The first one is about triangulation in etiological epidemiology, and triangulation is the practice of strengthening causal inference by integrating results from several different approaches, where, and here is the main point, each approach has different key sources of potential bias. And consistent to this view, the second paper advocates the use of a pluralistic approach. A pluralistic approach means integrating diverse types of knowledge. So causal inference means defining a causal question, identify the estimation approach, being transparent about the assumption, and then integrate different pieces of evidence to get the answer. And life course epidemiology is really a perfect, a good setting, a fantastic setting in which to use causal inference methods. And there are several features that facilitate the use of causal inference. Exposure data are obtained prospectively. Both cohorts are inception cohorts for what regards postnatal exposure. Repeated measurement, we have repeated measurements of the exposure, repeated measurements of the outcome. The follow-up duration is typically very long. Typically, we have in life course epidemiology, at least in both cohort research, we have availability of biological samples that can be used, for example, to define genetic instruments or to analyze molecular mediators. These studies are typically multi-purpose studies. That means that they have a lot of data, very rich in data, and so confounding can be controlled quite well. And then there is a long tradition of international collaborations, which definitely help causal inference approaches. We have several potential methods that can be used, and you have here a few examples: negative controls, for example, negative exposure and outcome controls, within siblings comparisons, mediation analysis, non-genetic instrumental variables, etc. But all these methods, and in general causal inference, needs that we are transparent and explicit, and we have assumptions about the data generating process. So it is important to be explicit about the assumption and knowledge on the system to be studied. And we can do that, for example, using graphical tools like the direct acyclic graphs that you can see here in these slides. In these slides, we have an exposure E, an outcome Y, and C is a confounder, Z is an instrumental variable, and I is a proxy of E. And having a graph like this one may guide the decisions and also allows to be transparent about the underlying assumptions. And now I will give you two examples in which, with the help of the DAGs, we reason about the causal structure, and we apply causal inference methods. And my two examples will be about mediation analysis in life course epidemiology and about baseline selection and collider bias. So mediation analysis, that you can see here in these slides, mediation analysis life course epidemiology is becoming more and more popular and can help answering different questions. Here you have three examples. The first one is to strengthen causation and to reconstruct the pathway that goes from the exposure to the outcome. And here you have exposure and epigenetic effect and an outcome. So this is an example. Then mediation analysis can help to study whether it is possible to mitigate the effect of an exposure on an outcome, for example, socioeconomic position, then the mediator, and then the outcome. We might act on the mediator to block the effect of a socioeconomic position on the outcome or to mitigate it. And then it also helps study mechanism answering questions like the one you can see here. So is the effect of maternal obesity on cancer risk explained by birth weight? Now I'm going to show you some assumptions that are really needed for mediation analysis. I'm going to do this using some DAGs. So the first point is about mediator outcome confounding. And here you have an exposure and an outcome, and we want to analyze the direct effect of the exposure to the outcome and the effect mediated by the mediator. And if we want to do that, then we should also consider all the variables like the L here, which are causes of the mediator and the outcome, and they act as mediator outcome confounders. So if we want to decompose the total effect into direct and indirect effect, we need to adjust for the variables like the L variable here. And in life course epidemiology, since typically the selected mediators are multifactorial variables, then there are a number of candidate L's or mediator outcome confounders that should be considered in the analysis. And things can get more complicated when these variables, so the mediator outcome confounders, are also affected by the exposure, as you can see here in this DAG. So this scenario depicted here is called intermediate confounding. And it's rather complicated to take intermediate confounding into account in the mediation analysis, because if I adjust for L, then I will block part of the effect of the exposure and the outcome, part of the direct effect, the one that is not mediated by the mediator, and goes through L. So this pathway here, down here, will be blocked. But if I don't adjust for L, then M the L will still act as a mediator outcome confounder. So whatever I do in this case, I can get biased results. And there are solutions to this situation, for example, considering L and M as multiple mediators, but things can get complicated. And the third point I'd like to make regarding mediation analysis is about the choice of the mediator, which of course depends on the research question, but sometimes it might be tempting to choose a mediator that is a proxy for the exposure. So it's strongly linked with the exposure, as you can see here in the bottom part of the slide, forgetting about the second part of the pathway, which is the effect of the mediator on the outcome. And in presence of exposure misclassification, then the indirect effect may be overestimated, especially if M is a strong proxy of the exposure. And what can happen is that the mediator captures some of the effect of the exposure on the outcome. So is the mediator a cause of Y becomes a crucial question in mediation analysis that sometimes is forgotten. And this was about mediation analysis, just to give an example of the causal thinking underlying the analysis. And now I'm going to speak about the second example that will be baseline selection in cohort studies. So baseline selection in cohort studies, I've been working on this topic for quite a few years, and it can be classified in two types of selection. The first one is so-called intentional selection, in which the source population is restricted to a specific subgroup of the population with specific characteristics. A famous example, historical example of this could be the British doctor study. And then we have unintentional selection, which is due to the participation of the people at baseline. So low baseline response proportion will induce unintentional selection in a cohort study. Interestingly, when we have this type of selection, unintentional, intentional selection, if this selection depends on the exposure under study and on the risk factor for the disease under study, like in this diagram here, and we restrict on the selected people, then this can induce collider bias, which will cause an exposure risk factor association. So basically, the selection alters the underlying confounding due to the risk factor, and the risk factor then should be adjusted for in the analysis. This risk factor, we can say that it becomes a confounder due to the baseline collider bias. We have now understood that collider bias may occur also in cohorts that are representative of the general population. So apart from intentional and unintentional selection, also the general population is subject to selection processes that might be associated with exposure under study and disease risk factor. And these selection processes could induce an association between the exposure and the risk factors because of collider bias. And the fact that these selection processes occur in the general population have been shown in this recent article that we have published last year, in which we analyzed the data from the Piedmont region, and we assumed to carry out a birth cohort study, which is based on pregnant women. We assumed to do this study in the whole population, so with no intentional or unintentional selection. Nevertheless, as you can see from these slides, there are several factors like age, educational level, occupation, number of components in the family, and place of birth, which are determinants of becoming pregnant or being pregnant in the general population, so they can act as risk factors and that induce the selection into the cohort. So I go back to the previous slides in which we had the exposure, risk factor, disease, and here the selection. And now I'm just mentioning here that the selection at baseline can be induced by intentional, unintentional selection, but also by selection processes in the population that can induce the baseline collider bias that is depicted here in these slides. So this second example brings me to the conclusions, very short, of this short presentation. First of all, but I want to say that some features of life course epidemiology facilitate the implementation of causal inference methods. Then that each method has its own assumptions and limitations. There is no gold standard, and this is the key point. We have to use more than one method and compare the results. And finally, we need still methodological development, and above all, we need to apply the different methods. So more applications of causal inference approaches in life course epidemiology are actually needed. And I would like to thank you. I also thank Life Cycle Project, in which I coordinate the methodological work package. And thank you for your attention, and goodbye.
Hi, I'm Jill McKay, Associate Professor at Northumbria University, based in Newcastle upon Tyne in the UK. I'd like to thank the meeting organisers for asking me to share with you the research we've been carrying out in exploring the environmental contribution to the molecular profiles of childhood leukemia. Throughout my academic career, I have been interested in the developmental origins of health and disease hypothesis, whereby there is growing evidence from both animal models and epidemiological studies suggesting that the environment experienced in utero and early life is able to alter programming mechanisms, and in doing so can influence long-term health. As such, individuals may be more or less susceptible to particular disease outcomes depending on their exposome during development. Of course, this paradigm is likely to be highly relevant for childhood cancers, given the earlier onset of disease, and so when I moved into the field of childhood leukemia from a background in molecular nutrition, this was where my interests were focused. We know from the epidemiological evidence that there are some associations between early life exposures, both in utero and during early development, that may influence risk of leukemia. Whilst there is stronger evidence for a role of some exposures, such as radiation and possibly maternal alcohol intake, the associations for other exposures remain weak and inconclusive. This, of course, is in part due to the difficulty in assessing these relationships due to the lack of accurate exposure data and the lack of power for these studies. Currently, it is not clear what the underlying mechanisms for these potential associations are. Understanding the influence of these exposures on the molecular mechanisms that may drive or contribute to disease will not only help us understand risk, but also may increase the evidence that these factors influence childhood leukemia risk. Of course, additional evidence to suggest leukemia is initiated during pregnancy is the early onset, particularly for acute lymphoblastic leukemia, which typically develops between the ages of 2 to 4. In addition to this, the presence of some of the initiating genetic events, such as chromosomal translocations, having been observed at birth, is suggestive of an in utero origin. It is plausible that environmental factors may influence the genetic initiating events, such as translocations, but there has been limited research in this area, and I'll come back to that later in this talk. However, since the frequency at which these translocation events have been observed in the general population is at a much higher rate than the manifestation of ALL itself, this suggests that additional mechanisms must contribute to the development of leukemia and ALL. We have been and continue to investigate the potential that epigenetic mechanisms may contribute here. So epigenetic mechanisms may be important in this context as we know they are established in utero and develop during early life. But we also know that they are modifiable by environmental factors. Therefore, development is a key period at which environment can influence the plasticity of epigenetic marks such as DNA methylation. As the function of epigenetics is in the control of gene expression, changes to these patterns has the potential to cause dysregulation and therefore manifest as changes in cell function, which may ultimately impact health. We also know that epigenetic marks, including DNA methylation, are present in all cancers, including childhood ALL. Therefore, they are likely to be a potential mediating mechanism between exposures and disease. And indeed, a little while back now, we investigated this hypothesis that DNA methylation may act as a potential mediating mechanism between environment and leukemia development. This work is published so you can read the full paper, but to give you a quick overview, we used a meet-in-the-middle approach in this study. As such, we identified genes which were susceptible to changes in methylation in response to environmental factors that have been considered to influence ALL risk, and compared them with genes which had altered methylation in leukemia itself. To do this, we used environmental and epigenome-wide data for over 800 children at birth from the Avon longitudinal study of parents and children known as ALSPAC cohort. And we took methylation data for ALL from the published literature. We filtered methylation changes for the directionality of effect, looking for concordant changes for risk factors such as radiation and smoking, and filtered for discordant changes for protective factors such as maternal folate intake. Using hypergeometric tests, we found that for maternal radiation exposure, maternal alcohol, and maternal sugary caffeinated drink consumption during pregnancy, it was unlikely that the overlap in methylation changes were due to chance, and therefore DNA methylation had the potential to be a mediating mechanism for those exposures. But whilst discussing this work with colleagues at another university, I was asked, but what about the first hit? What causes or what triggers translocations? Is there some environmental influence about that? And I couldn't really answer that question, but it nagged at me ever since. So I went away and did some digging, but the fact is that the causes of chromosomal translocations really still remains unclear. We know that these are rare events which form as a result of chromosomal breaks, which may occur due to replication errors or stress, and that these errors and errors in subsequent DNA repair lead to the incorrect portion of the chromosome being attached. Whilst there is some limited evidence to suggest that exposures such as smoking and pesticides may influence translocation rates, there's no real equivocal evidence for this. And moreover, data are lacking for most exposures that have been associated with childhood acute lymphoblastic leukemia. So, we therefore wanted to explore if leukemia-associated exposures contribute to chromosomal translocation events, and if different exposures influence different types of translocation events. To investigate this, we've chosen to look at 4 exposures as a starting point of our investigations. We've chose benzene as the major carcinogen in cigarette smoke, but also being present in paint and air pollution, which are also potential risk factors for acute lymphoblastic leukemia. Moreover, benzene exposure has been linked to occupational AML in adults and has been associated with the RUNX1, RUNX1T1 translocation. As it can cross the placental barrier, the fetus can be exposed. Likewise, cotinine, the major metabolite of nicotine, can also cross the placenta and has been shown to cause chromosomal damage. Meanwhile, folate deficiency has been associated with breaks in DNA and DNA repair problems, whilst caffeine alters genomic stability and can act as a topoisomerase inhibitor, which can increase the likelihood for double-strand breaks. So we took these 4 exposures and we want to investigate them for the association with translocation using a cell line model. So this slide shows an overview of the design of our in vitro experiments. We've used NOM6 cells, which we selected as a pre-B ALL cell line, which don't contain any of the common ALL translocations that we wish to measure. For benzene, cotinine, and caffeine, we exposed these cells to various concentrations of these factors for up to 4 days. We extracted RNA at both 2 and 4 day time points for 3 biological replicates. We then carried out RT-PCRs for 2 common translocations, RUNX1, RUNX1T1, and TCF3, PBX1. The range of exposure levels we have used across these studies have been designed to mimic physiological levels associated with various levels of exposure in human cohorts. The design for our folate deficiency experiment is slightly different, as it takes 4 days for the internal folate stores of the cells to become depleted. We therefore grow cells for 4 days in medias containing various concentrations of folate, only harvesting cells at the end of the experiment. So we have one time point only for this design. In our results so far, we have observed translocation events for both RUNX1, RUNX1T1 and TCF3 PBX1 for both benzene and cotinine exposures. Here, each of the X's in the box represents observing one translocation for one of the biological repeats. Whilst RUNX1, RUNX1T1 events appear to be more frequent at higher levels of exposures of cotinine and benzene that are associated with smoking and combined occupational exposure, TCF3 PBX1 events appear to be more frequent with lower levels of exposure that we see in non-smokers. We observed fewer translocation events with caffeine, with only TCF3 PBX1 being observed with medium exposure levels over 2 days and very, very high levels of caffeine over 4 days. TCF3 PBX1 translocations were also observed with lower and depleted levels of folate, whilst one RUNX1, RUNX1T1 translocation was observed with high folate levels. Reviewing the data in terms of the frequencies of translocation events in response to these exposures, benzene exposure followed by variation in folate exposure appear to be associated with the most events. Additionally, the frequencies of a different type of translocation varies with exposure. To summarise, in this preliminary data from our in vitro studies, we have observed at least one translocation event in our cells in response to some level of each of the exposures tested, with benzene exposure triggering the most frequent number of events and more likely to trigger RUNX1, RUNX1T1 translocations. This therefore may suggest that different types and levels of exposure may be associated with different translocation events. Further experiments are ongoing to test the reproducibility of these findings, as well as determining the exact sensitivity of the RT-PCR assays to pinpoint the minimum number of cells required in a population that need to have the translocation for it to be identified. We also wish to test in additional cell lines and for additional translocation types using these in vitro models. Whilst we may be able to provide some proof of principle for the relationship between exposures and translocation using these models, we still wanted to be able to assess the exposure-translocation relationship in a human context. However, this is fraught with problems and difficulties. Of course, some studies have investigated the relationships between cytogenetic groups where environmental data have been available, but as we know, often the environmental data can be vague and power is a real problem. The large birth cohorts can offer excellent opportunities to study this in terms of exposure data. However, due to the rarity of the translocation events and rarity of leukemia, hundreds of samples would need to be screened to test these associations. As well as the obvious cost implications, there are also other issues around measuring these translocations. In our cell line studies, we've used RT-PCR requiring RNA, which is not stable over time and therefore not suitable for historic human cohorts. Whilst there are DNA-based methods available, these either are prohibitively expensive or, where costs are modest, only allow for the investigation of single translocation types. We therefore tried to think of some potential solutions to this issue. We considered an ecological type study. However, our concerns here were the skewing of data depending on the quality of the cytogenetic data available. And this might particularly be a problem for data from low middle income countries. So instead, we applied our previous approach. We've applied our previous approach using epigenetic biomarkers as an intermediate to investigate the relationship between cytogenetic subtypes and environment. So here we've adapted the meet-in-the-middle approach previously employed, increasing sensitivity and specificity to assess if individual CpG methylation rather than methylation at the gene ID level is altered in response to exposure, and if this methylation change is also present across different disease subtypes. Again, we used the analysis we previously carried out within ALSPAC for our environmentally associated methylation changes, and used methylation data from one of the most comprehensive studies of over 700 childhood leukemia cases, as it utilised the same Illumina 450K array platform to analyse methylation as ALSPAC did. While significant overlaps between the data may indicate exposure-associated methylation as a mediating mechanism for subtype-specific disease, it may also suggest the exposure itself is more likely to be associated with a particular subtype, and therefore potentially could contribute to the underlying genetic event associated with that subtype. Before investigating the subtypes, since this new analysis was more sensitive in investigating methylation of the specific CpGs rather than gene-level changes, we compared the new CpG level analysis across all subtypes with the previous gene-level analysis we'd carried out before and published. Whilst the number of sites of methylation change were fewer and the significance decreased, in the main, the same exposures were found to have significantly overlapping methylation change in the more sensitive CpG analysis. We then went on to carry out our subtype analysis. 10 subtypes were investigated across our range of exposures. For ease of presentation, only the subtypes and exposures where potentially significant associations were found are shown here. Where data are missing in the table, there was a lack of association for overall overlaps, and therefore further investigation taking into account the directionality of methylation change was not carried out here. Where radiation and alcohol had previously shown significant overlaps when all subtypes were analysed together, the subtype-specific analysis may suggest that these exposures may be more likely to influence specific subtypes. For radiation, TALL and 11q23MLL and undefined subtypes show significant overlaps. And for alcohol, TALL and ETV6RUNX1 show significant overlaps. Where previously we saw no significant overlap for maternal smoking, with our subtype analysis for 11q23ML and for undefined subtypes, there were significant overlaps between CpGs with altered methylation associated with maternal smoking throughout pregnancy. This may suggest that different exposures may influence different subtypes through epigenetic drivers, and or different exposures may act as different risk factors for the underlying genetic event. However, perhaps one of the main limitations here is the constraints of the epigenome-wide association data used to identify the methylation targets associated with exposures, as this was limited to the sample size of the ALSPAC study. Therefore, refinement of these novel techniques through the use of more defined methylation signatures for both exposures and cytogenetic subtypes are likely to be useful tools for future studies to understand the relationship between exposures and leukemia. To summarise, our in vitro models provide preliminary proof of principle data for a relationship between ALL risk exposures and translocation events. Development of these models may help pinpoint which exposures influence which translocations, what levels of exposure can cause these events, and also be used to investigate the interactions between exposures in risk of these events. They may therefore be useful in informing human studies in terms of which translocations to investigate in the context of which exposures, and perhaps which are the likely confounders to correct for or interactions to investigate for. Meanwhile, our meet in the middle studies provide evidence that DNA methylation is a likely mediating mechanism between exposures and ALL, and may be useful to improve understanding of the relationship between exposures and subtypes, with methylation used as a proxy marker of exposure. Data from human studies could be used to inform the development of robust methylation signatures that could be tested in vitro. As such, none of this work stands in isolation, and only in joining the pieces of the complex puzzle together will we understand the complex relationship between exposure and disease. Of course, to do so requires collaboration and interdisciplinarity, and as such my ethos is to be highly cooperative and open to new partnerships. If anyone would like to contact me with any questions or to discuss any aspects of the work, please do so by the email given here. I'd like to finish by thanking everyone who's been involved in the work. The main contributor for this has been the work by Jessica Saville that's been described here for the in vitro and the meet in the middle approach in the subtype analysis. I'd like to thank her, along with Jessica Nordland, who's been kind in providing us data for this analysis, as well as Caroline Welton and the ALSPAC team, who've made all of this work possible. Thank you.